Okay. Now we switch to branch prediction because your lab is on branch prediction. And I wanted to give you a lecture on a topic that has fascinated many people for a really long time. It still fascinates many people, but it's a very, very hard problem at this point because so much progress has been made on branch prediction amazingly. But hopefully I will convince you that there may be need for even more progress going forward. The question is, how do we do that? Okay, because before we start, you know that there's an exam coming up, right? Or maybe you didn't know. We have 2 exams in this course. The first one is the simpler one, I guess. It's November 8th. It's going to be in class. I guess we have only one class, November 8th. That's a Thursday. Did we announce it online? Okay, now it's announced. And the other exam is the last day of classes, basically, December 20th. I see eyes rolling, so it should be okay. Yeah. Okay, basically, be prepared. I think you're doing homeworks. Are people doing homeworks? Okay, that's good. Is it fun? It's basically to prepare you to understand the material. Even though there's a lot of questions, it's good for you to understand the material. In the end, though, the grades don't matter that much, I believe, as long as you learn the material. But homeworks don't account for much of the grade anyway, if you look at it. Hopefully you're doing the reviews as well. Are they fun? Yeah? Okay. Are the labs fun? Yeah? Okay, I hope something is fun. Yeah, labs, if you haven't done RTL before, it may get you... you'll need to learn about it. As I mentioned earlier, you should study on your own. This course, you need to have done RTL before a little bit. But of course, like with any other lab, you'll spend time understanding the lab, debugging the lab. But once you understand it, it's not that hard. Just need to get to that point. Okay, exam. Basically, we'll have all the material covered in the course that can be part of the exam. That includes the lectures, certainly, the labs, the homeworks. But we'll see. We still have time to get there. Okay, well, last week, this is what we've done, basically. Or last week, and maybe a little bit before the last week as well. We talked a lot about DRAM. We talked about cutting-edge issues in latency, retention, and new uses. You had some guest lectures of really cutting-edge research in the area. We're going to get back to DRAM after we're done with control flow. And we talked about SIMD. We're going to get back to that also. SIMD processing, if you remember, graphics processing units. And then we talked about intro to genome analysis. So hopefully that gives you a broad overview of what different things that are happening in architecture today. Of course, we cannot cover everything, but these are some examples. Even this by itself shows that there's a lot of breadth and important topics that are there in architecture today. So we're definitely going to get back to these 2 later on. We may or may not get back to this, but you know whom to talk with if you're interested in that topic right now. Okay, today and maybe tomorrow, we're going to talk about control dependence handling. We're going to talk about the problem and hopefully 6 solutions. I cannot promise all 6 right now, but maybe certainly branch prediction we're going to cover today. And we'll, hopefully, if time permits, we're going to go to other methods of control dependence handling. And as I said, this is a topic that has fascinated many, many researchers. And a lot of the things that I'm going to describe went actually into processors. The processors that you're using today are really using very, very sophisticated branch prediction methods. And we'll talk about that. And they may still need more. Especially if some of the cores that you have are actually very powerful. As long as you stick to the control flow paradigm, you need some way of predicting those branches because they get in the way. Okay, these are some readings. Actually, I was debating whether I should put one more over here, but I'll make it recommended for now. This is combining branch predictors. This is the seminal paper that introduced hybrid branch prediction. This is the paper that really introduced 2-level branch prediction, which was a huge step from the 1-level branch prediction, which you will also talk about. And this was one of the Test of Time award winners from the micro conference. We're going to actually see a bunch of Test of Time award winners during this lecture. And there's another paper that I thought about giving as a required reading, but I decided not to in the end so that I don't overload you. But I recommend that you read it. It's basically branch prediction using perceptrons, machine learning, very simple form of machine learning. We're going to talk about that. And that has also influenced industry, and that is part of some processors today. Okay, so hopefully it'll be fun. And these are some recommended readings. If you've taken digital circuits, actually, I suggested this reading. So if you've already read it if you've taken digital circuits, but you may want to read it again. And this is a paper that we will also talk about, because this adopted the hybrid branch prediction concept for the first time. Okay, so basically we need to start with pipelining if you want to talk about branch prediction. And this is directly taken out of the digital circuit slides. There are a bunch of issues when you're designing a pipeline processor. You will realize that when you're doing the lab, or you may have realized that if you've done the labs in the past, right? Basically, you need to balance work in pipeline stages. We're not going to talk about that. This basically try to equalize the work such that you can maximize the efficiency of the pipeline. How many stages do you have? What is on each stage? We're not going to talk about that. That's very interesting. But a lot of these things are relatively well known right now. This one is a bit harder part. Once you've designed the pipeline, you need to keep the pipeline correct, moving, and full in the presence of events that basically disrupt the flow of the pipeline. Right? And this amounts to handling dependencies. Dependencies are also called dependencies. I like dependencies here, but sometimes I say dependencies. Data or control. And we're going to focus on control here, but data is also very important. And this also you need to handle resource contention somehow to satisfy this. Meaning you need to handle long latency, multi-latency operations. And we're going to get back to this, as well as the data dependencies later on in these lectures, and take a memory perspective as well as a processor perspective to see how we can handle these long latency operations. Okay, you need to handle exceptions and interrupts, and we've covered that in digital circuits. We're not going to talk about that right now. And you need to improve pipeline throughput somehow, and this is important for minimizing stalls. So these are actually related, these two over here. Okay, what are the causes of pipeline stalls? Stall is a condition in which the pipeline stops moving. Right? For some reason, you're stuck there, you're stalling, and you cannot move the front end of the pipeline. And this happens due to three major reasons. Resource contention is one, dependencies is another, and long latency operations is another. And we're going to tackle dependencies especially today. As I said, this is also called dependency, or less desirably hazard. Hazard sounds really bad, but hazard is something if you don't handle something well, it becomes hazardous, right? But dependence is really at least the data and control dependence are very fundamental to the program. They are there for different reasons. You need to have a dependence between this instruction and this instruction, and you need to satisfy that dependence. That's fundamental. That's not really hazard in the end. And control dependence is so fundamental to von Neumann architecture, right? Every instruction is control dependent on the previous one, right? That's sequential dependence. So that's ingrained in the nature of the execution paradigm. Okay, so basically they dictate ordering requirements between instructions. And resource contention is also sometimes called resource dependence. So this is not a really true dependence, but this is really not fundamental to the program semantics. And we will treat it separately, and we have treated it separately, but we're going to get back to resource contention, especially in multi-core processors later on. Okay, so in this lecture, we're going to focus on control dependence handling. So this was a good overview, hopefully, to jog your memory on pipelining. Let's talk about control dependence handling. So basically, the key question over here is very simple. What should your fetch program counter or instruction pointer be in the next cycle? You're fetching something in this current cycle, and you want to keep the pipeline moving, correct and full, meaning that you need to know what to fetch in the next cycle. And this is the question that you need to answer while you're fetching the current instruction. You need to figure out what's the next instruction. Right? It sounds very simple, right? Answer is, of course, the address of the next instruction that you're going to execute. But do you know the address of the instruction that you're going to execute? Basically, all the instructions are control dependent on the previous ones in the von Neumann model, because you have sequential dependence. The instruction, if the fetch instruction, current instruction that you're fetching, is a non-control flow instruction, that means that next fetch PC is the address of the next sequential instruction. Right? Basically, if you're used to MIPS, for example, it's PC equals PC plus 4. The next PC is PC plus 4, assuming the fetched instruction at this current cycle is a non-control flow instruction. Simple. This is easy to determine if you know the size of the fetched instruction. Now you encounter one problem, right? If you have a variable length ISA where all your instructions are not the same size, this PC equals PC plus instruction size is not even easy because you're just fetching the instruction right now from the instruction cache. You haven't even seen the instruction yet. You don't even know if it's a control flow instruction, let alone its size. So you would need to predict its size, right, to figure out PC equals PC plus size. So we're not going to talk about that problem actually here. We're going to talk about an even more difficult problem. That problem needs to be solved, even if the fetched instruction is a non-control flow instruction, right? x86 is an ISA where an instruction can be anywhere between 1 byte to 16 bytes. Maybe even 17 right now, actually. They keep changing the ISA, so I don't know. But definitely between 1 and 16 bytes. If you don't know what's the size of the instruction you're fetching right now, you wouldn't know what to fetch in the next cycle. Okay. But the bigger problem is if the instruction that is fetched is a control flow instruction, then you need to figure out what should be the next instruction to fetch. Not the size of the current instruction, but what is the PC of the next instruction. In fact, we do not even know whether or not the fetched instruction is a control flow instruction, right? Because we're fetching from some PC, we need to fetch the instruction first from the iCache. We haven't even decoded yet. Next stage is decode. Okay, so you need to keep some information around to be able to do that. So we're going to talk about that. So that makes the problem harder. Okay, basically these are the different branch types. We're going to focus a lot on the conditional branches. This is just to jog your memory again. You can have conditional branches. You don't know the direction at fetch time, which way it will go. You have two possible fetch addresses, and the next fetch address is resolved later in the pipeline. Basically, you cannot, one option is to wait until the next fetch address is resolved, but then you're basically causing a lot of pipeline bubbles. Okay, unconditional branches, always taken. You have one fetch address, and the next fetch address could be resolved in decode time, because it's usually PC plus offset. Calls are very similar to unconditional branches, actually, but they're special in the sense that they're usually matched with a return. Return is a form of indirect branches. They're always taken, but they could return to many different call sites. And these are usually register dependent, meaning that you know the return address at the end of execution of the instruction. And finally, indirect branches are very similar to returns, but they're not as special as returns because you could basically jump to anywhere. Actually, that's true for returns also, but you need to use a special register usually to return to. But basically, different branch types can be and should be handled differently. I don't have a conditional indirect one here. That's actually the worst. If you have a conditional indirect, basically you don't know whether you will take the target. Basically it's conditional indirect. That makes this much harder. But you can imagine techniques to do that. But we're going to focus a lot on the conditional branches for now. Okay? Okay, so it's basically critical to keep the pipeline full with correct sequence of dynamic instructions. And there are many potential solutions people have developed. We're going to look at a few of them that are not reasonable to begin with, like stalling the pipeline until we know the next fetch address. That's not going to be reasonable. Guess the next fetch address. That's what we're going to focus a lot on. Employ delayed branching. Basically, branch takes effects after some number of instructions or after some number of cycles. You basically keep fetching, and after n cycles, you fetch this branch, it takes effect. So we're going to talk about that solution later on, this employed in Spark, for example. Or do something else, fine-grained multi-threading. We covered a lot of these solutions actually in digital circuits, so you may know some of these. And eliminating control flow instructions is a good solution also, predicated execution. We'll talk about that if you can do that. And fetch from both possible paths. So as opposed to taking one path, maybe you go for both paths, right? Now you need multiple pipelines to be able to do that. So the complexity increases. So this is called multi-path execution. And you could, of course, combine these different techniques as well. Let's see where we get. Any questions so far? Is this going to be fun? We're going to cover a lot of ideas, actually. A lot of fun ideas. But let's start with this dumb thing, which basically goes against pipelining, if you will. And let's see how much performance we lose. Basically, the key idea here is stall the fetch until next PC is known. And we're not even going to look at control flow instructions yet. Basically, control flow and unconditional branch instructions. What happens to the pipeline if you do that? Well, when is next PC known? Next PC is known after this instruction is decoded, and you figure out It's a non-control flow instruction. You know its size, and you basically say PC equals PC plus size, right? Which means that you've just wasted the slot. You cannot fetch an instruction over here. You need to fetch the instruction in the next cycle. That's true for that instruction as well. You need to fetch the next instruction in the next cycle, in the next cycle, in the next cycle. Basically, what you've done is you've lost 50% of your pipeline throughput. You're fetching an instruction every other cycle. This is stupid, clearly. You don't want that if you're designing a pipeline processor. That's why we need to do something else. But let's talk about the extent of the problem first. I think this is very instructive, and I was very proud of myself when I developed the slide. So let's see. Basically, let's assume some things. You have control flow instructions, branches that are reasonably frequent. You have 15 to 25% of all instructions. The problem is next fetch address after a control flow instruction is not determined after n cycles in a pipeline processor. Basically, you need to wait for n cycles in a pipeline processor. Now, this is called the minimum branch resolution latency. If let's assume that we're fetching W instructions per cycle. If the pipeline is W wide, in superscalar execution, you can be W wide. In VLIW also, you can be W wide. Basically, a branch misprediction, let's assume that you're predicting the branch. If you mispredict it, you wasted n times W instruction slots. W on the number of pipelines, let's say, and n in the pipeline depth. So pipeline depth times pipeline width. Right. Now we're going to calculate how many instructions we wasted. So we're going to assume n equals 20 pipeline stages, which is not unreasonable. Some of the Pentium 4 incarnations had 30 or more stages actually. Currently we're probably around 16, 17, I don't know. Depends on the processor. Let's assume your fetch width is 5. You're fetching 5 instructions per cycle. And assume that 1 out of 5 instructions is a branch. And assume that each 5 instruction block ends with a branch, so things are nicely aligned. Let's take this calculation. How long does it take to fetch 500 instructions? I picked these numbers so that calculations are easy. So if you're 100% accurate, and you're fetching 500 instructions, and all of your branches are predicted accurately, correctly, that means that you're fetching 5 instructions per cycle, and you're spending 100 cycles to do that. And all instructions you fetched are on the correct path. Make sense? Right. Another way of doing the calculation is you have 500 instructions, 1 out of 5 is a branch. You have 100 branches over here. 100 of them are correct, so you don't go on the wrong path. So all of the instructions that you fetched are on the correct path. This is reasonable. Right. No wasted work. You can calculate your IPC instructions per cycle, which is 500 divided by 100, right? 5 instructions per cycle. Perfect. Now let's go down to 99% accuracy. If you are 99% accurate, 1 out of those 100 branches that you're supposed to fetch goes on the wrong path. Everything else is on the correct path. Meaning that you still need to spend 100 cycles to fetch all of the correct path instructions, but 1 out of the 100 branches, you go wrong path and spend 20 cycles. So basically you need to spend 120 cycles to fetch all of those instructions that you need to fetch. And you fetch 20% extra instruction, and if you really want to calculate your IPC, that's your IPC. Okay, simple. Now let's go to 90%, which sounds good, right? You're predicting these conditional branches, and 90% you're accurate. Sounds better than definitely a random coin flip. Well, if you do this, you still need to fetch 100 cycles on the correct path, but now 10 out of those 100 branches are incorrect, which means that you're spending 20 cycles on the wrong path for each. Now you need to spend 300 cycles to fetch all of those instructions, which means that you just fetched 200% extra instructions. That sounds terrible. And your IPC plummeted to 1.66, right? Even with 90% accuracy. So that's how you get from 100% to 90%, your IPC goes from 5 to 1.66. That sounds terrible. Well, what could be worse is 60% accuracy, which is still better than a random coin flip. Basically, you're doing this wrong path execution for 40 of these 100 branches, and you're basically spending 900 cycles to fetch 500 instructions, and you've increased your extra amount of work in the fetch engine by 800%. And your IPC is now below 1. So this sounds terrible now. So clearly we want to be close to 100%, especially with a pipeline like this. And this pipeline is not too aggressive, I would say. Maybe if you put n equals 30 and w equals 8, you become more aggressive, which means that you're wasting 240 things on the wrong path. Well, one cycle. Okay. Does that make sense? So this is the importance of the branch room. This is why people have focused on this for a long time. You don't want to be here. You really want to be closer to 100%. Okay, so how do we get there? So branch prediction, the basic idea is very simple. You guess the next instruction to fetch. It's a guessing game, if you will. You get to this branch can go here or here. If you do stalling of fetch, you need to wait, and this is a conditional branch. Stall fetch actually has much worse impact than we previously showed in that diagram. Basically, you need to wait until this branch is resolved, which means that it's at the end of its execution, and you can only fetch after 4 cycles in this case. And in this example, it basically takes some number of cycles, I think 12 over here. But if you do branch prediction, if you're correct, after this branch, you're able to fetch the predicted instruction, and you keep the pipeline full. And if you're correct, that's great. You basically reduced 12 cycles to 8 cycles over here in this example. And this is not even the steady state yet. Okay, but the problem is if you're incorrect, you need to get rid of some instructions. These should have been red. Somehow the color scheme broke. Okay, but basically you need to refetch. So if you're incorrect, you have an overhead. That's the misprediction penalty. So how do we do this fetch? Let's start with the simplest mechanism. Simplest mechanism is always guessing next PC equals PC plus 4. At this point, I'm going to assume that you know the size of the instruction that you're fetching, or you're accurately predicting it, which you could by consulting a separate table, right? A separate table basically tells you the size, because it's assuming you've decoded the instruction previously. We're going to talk about that also. But assume that the size is known, 4, let's say. You always predict the next sequential instruction to be the next instruction to be executed. And this is actually next fetch address prediction. This is a form of branch prediction. The problem is, it turns out you normally don't go to the next sequential instruction. You normally don't go to PC plus 4. If you have loops, you usually go to somewhere else, which is the target of the branch. And people have found out many, many times that most branches are taken. More than 60% of the branches are actually taken. And we're basically doing not taken prediction here. So the idea is to, if you have a branch predictor like this, if you're stuck, let's say, one thing you could do is actually you could change your software to maximize the chances that this next sequential instruction is the next instruction to be executed. Right? You have 2 targets for a branch. One is the next sequential one, and the other is somewhere else in the code. Try to make the next sequential one the more likely one to be fetched. And in the software, you could do this. You can basically lay out the control flow graph such that the likely next instruction is on the not taken path of the branch. Does that make sense? Basically, you have a control flow graph, which is, I don't know, if I do this, will I be recorded? I think so. Okay. Okay, that's a bit slow. I don't want to cover over here. Are you able to see this? But I need something. Okay, maybe. Okay, there it is. So this is can you guys see this? Basically, we have a branch. These are different basic blocks. This is the target. Well, this could be the target of the branch. And this is I guess if this is PC, this is PC plus 4. It's hard to write. Well, and if it somehow turns out that 99.9% you're going to the target, well, change the software such that this is not the target anymore, and this becomes a PC plus 4, right, in the layout of the address space. And this is the target. That way, well, you didn't change the 99.9%. That still stays the same. And now your prediction next PC equals PC plus 4 works correctly 99.9% of the time. That's the idea over here. It's a very simple idea. It's actually employed in many compilers, including GCC, and we're going to talk about that next. This is called profile-guided code positioning, and this is the seminal paper that introduced the idea in the Programming Languages Design and Implementation Conference. Makes sense, right? So hardware, maybe you can do the same thing that I just described in hardware also, and hopefully we're going to get to another idea that is also implemented in some of the processors that does it in hardware. It's called a trace cache, basically. You somehow cache the traces of executed instruction. If you already executed this path once, when you execute again, basically when you execute it once, store the trace of instructions that you've executed, and when you go back to it, just fetch from that trace, as opposed to going from somewhere, fetching from somewhere else. That's the idea. Okay, so we discussed this already. Basically, how else can you make this more effective? That's one idea. Well, two ideas actually. But there are other ways of making this more effective. You can get rid of control flow instructions or minimize their occurrence, right? How do you do that? One is you can get rid of unnecessary control flow instructions by combining predicates. So if you're doing, for example, multiple tests, if A is greater than 0 and B is greater than 0 and C is greater than 0, do this. As opposed to converting these to 3 branches, for example, you may actually have a combined branch for all of them. That way you get rid of control flow instructions now, and you get rid of the irregularity in the control flow. That's the idea, and many compilers also do that. Or you could convert control dependencies into data dependencies, and this is the idea of predicated execution that we will talk about. I'm not going to get into this now, but basically you can convert a branch into data dependency. And you could use that data dependence. Now you have another problem, which is how do you handle that data dependence, but that data dependence may be easier to handle. So we're going to talk about that. If you've seen digital circuits, you've seen predicated execution at least a little. Okay, so let's take a look at always PC plus 4. Basically, if the instruction, branch condition, and target is evaluated in the ALU, you keep the pipeline full. When a branch is resolved, what happens is branch target is fetched, assuming you're incorrect, and all instructions fetched since the instruction must be flushed. This is the incorrectly predicted instruction, right? So you have flush penalty. That's the idea, and you will need to implement this in your pipeline, basically. If you so whenever you have branch prediction, you need to ensure that branch mispredictions are handled correctly. And PC equals PC plus 4 is no different. You're predicting something, and you need to ensure that if you're wrong, you flush the correct instructions from the pipeline. So let's take a look at some performance analysis. This is very simple performance analysis with a single white pipeline, so it doesn't give you the impact of branch prediction in the small pipeline. Whenever you have small and narrow pipelines, short and narrow pipelines, you're not going to get much benefit from branch prediction. So assume that we have a correct guess, no penalty. Incorrect guess gets us 2 bubbles. And let's assume that this happens 86% of the time. We have 20% control flow instructions, and 70% of the control flow instructions are taken. That's how I got the 86% of the time over here. Basically, 20% of the instructions are control flow. 70% of the instructions are taken. If you're actually predicting the next instruction is not taken, you're incorrect 70% of the time. Right? That doesn't sound good. So your cycles per instruction otherwise would be 1, perfect pipelining, and you have a penalty on top of that for branches. 20% of the time, you're mispredicting, which means that for 20% of the instructions, control flow instructions, and 70% of them, you're wrong, and you add 2 bubbles for each of them. And that's how you get to 1.28 CPI, cycles per instruction. Hopefully this is a very simple calculation, right? So basically there are 2 issues here. One is the probability of a wrong guess, which is determined by the branch misprediction rate, and the penalty for a wrong guess, which is determined by how many instructions do you flush if you have a wrong guess. And you could actually get rid of the branch penalty by reducing either of those 2 penalty terms. You could either reduce the probability of a misprediction by having a better predictor, for example, or you could reduce the penalty. Actually, you could be always incorrect as long as you can correct yourself very quickly. Right? You can think of it that way. Now the problem is this penalty for a wrong guess is very difficult to get to 0. Let's take a look at that. So this is one example pipeline. This is actually similar to the pipeline you have. We want to resolve the branch condition and target address early. And this is what we would like to achieve. Basically, as opposed to having 2 bubbles, we want to have 1 bubble, let's say. So 2 bubbles, branch condition actually resolves somewhere over here. So I don't put that over here, but there should be a baseline pipeline where in the baseline pipeline, branch condition resolves over here, and as a result, you have 2 bubbles by the time branch condition resolves. And once the branch condition resolves, you can send the target address over here, and these 2 instructions are flushed, and the next cycle you can fetch from the correct target address. Now, if you want to reduce the probability of a penalty of a wrong guess, we want to move the branch resolution earlier. Can we do that? Yes, of course you can do that. Right? You can always lengthen the pipeline stage to do that. So this is exactly what we did over here in this picture. Basically, for branches, we added special hardware. This is branch equal, or branch greater than 0. You need basically a comparator between the source register and the destination register in MIPS at least. And you compare, and that comparison serves as your branch condition. And this is your target address calculation mechanism. You can calculate the target address actually, even potentially earlier. But let's calculate it over here. This is your target address. This is your branch condition resolution. And if branch condition resolution is different from the predicted branch direction, then you will use this target address to redirect the fetch engine. That's the idea. There's no reason you cannot do this, right? And actually it reduces your CPI to 1.14 as opposed to 1.28. Does that make sense? Of course, is this a good idea is always a good question. What is the answer? Usually the answer is it depends. And that's true in this case also. It really depends. It really depends on what you've done over here, right? Is this actually going to affect your critical path? Because here we're just looking at CPI, we're not looking at frequency. And remember, performance is always CPI times frequency. In this case, have we lengthened the critical path? I don't know over here, but very likely. Basically, now we've added this comparator after the register file access. So this stage will is probably going to take longer to perform. Not only that, but we're going to move that over here. So that's maybe the critical path. If that lengthens your frequency, that lengthens your clock cycle time, this may not be a good idea. In fact, you could actually move everything to the first stage, right? All of the branch prediction logic to the first stage, all of the branch resolution logic to the first stage, and get rid of branch prediction. But then you'll need to move all of this, and that will be your stage, and then your frequency will be much lower. Okay? So basically, the takeaway is reducing the penalty for a wrong guess is a good thing to do, as long as it makes sense to do. And usually the trade-off is by reducing the penalty for a wrong guess, you're, yes, reducing your cycles per instruction, but you're very likely also reducing your frequency. Okay, maybe you'll have fun with it in your lab. Okay, so let's talk about branch prediction in a little bit more advanced fashion. So we're going to focus on predicting the next fetch address now to be used in the next cycle. And this requires three things to be predicted at the fetch stage. By the way, before we go on, the reducing the probability, penalty for a wrong guess actually is very interesting. If you can somehow, so we have done some work in the past where what we wanted to do is basically figure out whether we're on the wrong path before the branch actually resolves. And what we wanted to do was anomaly detection. If you actually detect some anomalous condition in the pipeline, maybe that's an indicator of the fact that you're on the wrong path. We call these the wrong path events. For example, if one of your loads dereferences a null pointer, what's the probability that it's going to happen if you're on the correct path? Well, it could be, it happens if your program is buggy, but then you don't care about your performance. And it turns out that assuming your program is not buggy, the probability that that happens when you're on the correct path is 0, almost 0. I cannot guarantee it's not 0 because sometimes programmers do weird things, right? But it's basically 0. As a result, if you get a null pointer dereference, it's very likely that you're on the wrong path. And if your earlier branch didn't resolve before then, you can say, okay, one of my branches was mispredicted, so I'm going to take action. So there are actually really interesting ideas that could potentially be developed to figure out whether you're on the wrong path before your branch is resolved. But we'll leave that for another time. If you can do this much more accurately, that's always good to do that. But then there are also trade-offs here, predicting the next fetch address. So this requires three things to be predicted at the fetch stage: whether the fetch instruction is a branch, as we've discussed, the direction of the conditional branch, and the branch target address, assuming if it's taken, of course. So let's take a look at these different things. First, let me start with the branch target address and whether the fetch instruction is a branch. So the key observation is that the target address remains the same for a conditional direct branch across dynamic instances. As a result, if you already executed this branch once, you know its target address, store it somewhere, and the next time you see this branch, use that target address as your prediction. And you will be correct for the target address. And that's true for branches also. If a branch, if an instruction at a program counter is a branch, it's going to remain as a branch. Unless you have self-modifying code, which changes a lot of things, of course. And x86 actually does have self-modifying code. They still allow it. But ignore that for now. If you don't have self-modifying code, an instruction is going to remain as a branch. So the first time you execute the branch, record that it's a branch, and record its target address in a separate structure. And that's the idea over here. Store the target address from previous instance and access it with the program counter when you fetch it. This is called a branch target buffer or a branch target address cache. IBM calls the branch target address cache, BTAC. And this is the fetch stage with a BTB, I'll call it a BTB, cache of target addresses, and the direction predictor. Basically, we're going to take the program counter, the address of the current branch, use it to index a cache of target addresses, which will tell us whether there's a hit, and if it's a hit, we'll get the target address. And if it's also a hit, we know that this also in the past was a previously taken branch. Or we could insert non-taken branches target address over here as well, no problem. And concurrently with the access to this cache of target addresses, we're going to access the direction predictor, which is going to magically tell us whether this branch is predicted to be taken or not taken. And if it's predicted to be taken, and if we get a hit over here, then next fetch address should be the target address that's supplied by the branch target buffer. Otherwise, if it's not predicted to be taken, or if we get a miss over here, we're going to predict the next fetch address as the next sequential instructions address. So it's simple, right? But of course, what goes into here, especially here, will be very complicated. And this mux we're going to widen more, because this is just looking at conditional branches, right? What about indirect branches? There need to be some other prediction. What about returns? What about calls? There needs to be other prediction mechanisms, and there should be other inputs to this mux. And also, there's an input to this mux coming from the back end, which is where the branch is resolved, right? If the branch is resolved, and if you need to actually flush the pipeline, that path needs to be fed over here, and you need to have appropriate control in the mux saying that, oh, that's the highest priority event actually. You don't care what's happening here if you're flushing the pipeline from the back end. Okay, so that mux is now going to get wider, and this is going to get more complex. And we're going to use other stuff over here to index. So that's going to be fun. It's actually one of the most fun parts of the machine, and one of the hardest parts to design if you're designing a general purpose control flow machine. Okay, so more sophisticated ones, just to foreshadow what's going to come. We're going to use a program counter to get the hit and target address, but we're going to build a predictor that looks like this. It's actually used in many machines. You basically hash the global branch history, which direction earlier branches went with the program counter, and that is going to improve our prediction accuracy for multiple reasons. It gives you more context, and also it distributes the accesses to the direction predictor better. Have you guys seen this before? No? Who has seen it? Okay, some people. That's good. Most people have not. So if you've taken digital circuits, you would have seen it, but we're going to have fun with it. Okay, so that's the idea. So this is one form of sophistication, but it's not as sophisticated as what we're going to really build up to. So that's one idea. That's called the G-share predictor. And the rest is the same over here. Okay. So, okay, we said that we require three things to be predicted at the fetch stage. We said the third can be accomplished using a BTB. Target address computed, basically you remember the target address computed the last time branch was executed. And first can also be accomplished using a BTB. If BTB provides a target address for the program counter, then it must be a branch. That's the idea. Okay. Or optionally, you can store branch metadata bits in the instruction or cache memory. You can have a partially decoded instruction stored in the iCache. This is actually done in early AMD processors. In K5, for example, as opposed to having a BTB, they stored in the instruction cache information with metadata related to branch instructions. In fact, not only branch instructions, with every instruction. What they did was they had the size of an instruction in the instruction cache together with the instruction, partial decode. Because when you actually decode, when you actually bring an instruction into the iCache, they had a partial decode engine that basically quickly goes over the instruction and says, oh, this is the size of the instruction. And it writes the instruction to the iCache from the memory, and also the size. Now you've solved one of the problems that we've discussed, right? Even if you have a non-control flow instruction, you know the size of your instruction whenever you fetch, and you can have an adder in the fetch stage that takes your program counter, adds it to the size, and then feeds it back to your PC. Of course, it's not as easy because that adder takes time, and you lengthen your critical path potentially. So that loop is actually very sensitive. Okay, but this is one way that is also handled in some processors. So okay, now let's talk about the second one, which is the hard one. How do we predict the direction? We're going to go over a bunch of schemes. We've already gone over not taken, but I'll call these, some of the schemes, compile time or static, because compile actually has a lot of influence in these. Compile has influence in these also, but in a much more difficult way. So we're going to look at first simple schemes, and then we're going to look at more runtime dynamic schemes, and we're going to build up to other stuff, advanced algorithms like perceptrons. You guys ready for it? Maybe? Okay. Okay, let's look at the compile time ones. We've already talked about always not taken. This is simple to implement clearly. There's no need for BTB because you're not even predicting the target, right? Always not taken means you're always doing PC plus PC equals PC plus size, but you do need the size. And that's not a problem in ISAs that are fixed length. And no direction prediction. The problem is, as we said, low accuracy, 30 to 40%, if you're lucky, 40% for conditional branches. And you could improve this by having a smart compiler. Compiler can lay out code such that the likely path is the not taken path. That gives you more effective prediction. And as I said, this is already employed. Actually, much more sophisticated methods for increasing the probability that you're getting your correct path in the machines employed. We're going to talk about superblocks later on. Always taken is a bit more complicated. It still requires no direction prediction. So that complicated part is gone. And it gets you better accuracy, 60 to 70%. But as we discussed, 60% is not good enough, right? 70% is also not good enough. And the reason is backward branches, loop branches are usually taken. Imagine that you're iterating over a large loop that's taken 10,000 times. You're going basically to the target of the branch. And backward branches, the definition of the backward branch is a branch that has a target address lower than the branch PC. That's why it's called backward. It doesn't really need to be backward, right? Okay, but it basically indicates that branches that way. Okay, backward taken, this is also called loop branches, by the way. People have actually realized that it makes sense to predict taken if the branch is backward, because many of the loops are taken. You keep iterating in the loop. But if you have a forward branch, that's not as clear. As a result, they've developed this static scheme that says if the branch is backward, predicted taken, otherwise predicted not taken. Now for this, you need to figure out whether the branch is backward. First of all, you need to compare the target address to the PC of the branch. So there's a little bit more logic involved. But you could also store this information in the BTB, right? Whether it's a backward branch or a forward branch, it's one more bit. Okay, and it turns out that this actually has a slightly better accuracy than always taken. So what else can we do? Profile-based mechanisms are potentially more can buy you more. Here, basically, the key idea is compiler determines the likely direction for each branch based on a profile round. And it encodes that direction as a hint bit in the branch instruction format. Basically, you run the program once with some input and figure out, oh, this branch was executed 100,000 times and 78,000 times it was taken. And then you say, oh, this branch is likely taken. So I have a bit in my branch instruction format that says, what is the predicted direction by the compiler? And the compiler sets that bit to taken. And it does it for every branch. And assuming that profile is accurate, then now you're better, hopefully, because you're per branch based. You're not, if you look at these mechanisms, they're not adapting to the behavior of a single branch. They're basically very holistic, global. So the big benefit here is you get per branch prediction, more accurate than the schemes in the previous slide. But of course, there's a caveat. This is accurate if your profile is representative, right? If you profile the program and you got 78% taken rate for a branch with some input set, and when you run the program, you run it with a different input set, because if you actually had the input set to begin with, then you'd be very lucky. And that different input set gives you 0% taken rate. Now you've actually done the completely wrong thing, right? So basically your profile needs to be representative. Whenever you're doing profiling, the key thing is to have your profile to be representative. But if that's true, this actually buys you better accuracy. Now another downside of this, if the profile is not representative, you have a problem. But in addition to this, you need to have hint bits in the branch instruction format. And actually most ISAs have these hint bits today. It's not clear if they're fully used by the compilers, but they could be. It's also not clear that they're fully used by the hardware. The compiler can indicate this direction, but the hardware, if it has a better algorithm inside, it can ignore it, right? But this direction, this bit can be useful even if you have a very good algorithm in hardware, because sometimes you may have a branch prediction algorithm in hardware, but it takes a long time to train it, to get it to a stage where it predicts correctly well. But if you have this hint bit, while the hardware algorithm is training, you can actually use this hint bit. Just rely on it, right? Make sense? So we're going to talk about the warm-up time issues in prediction. Okay, so if you look at this, accuracy depends on dynamic branch behavior. These are not so good cases for the profile base, especially if you have 50% accuracy. For example, this one. The branch is taken 10 times. After that, it stops being taken. It starts becoming not taken. And because you cannot encode this with a single bit, you have a problem. You get 50% accuracy. Right? And this is another one. But you could easily figure this out if you had a dynamic branch predictor that adapts, right? Which we will talk about. It's another example, taken, not taken, taken, not taken. You get 50% accuracy over here. So this works well if the branches are biased. And we will see that most branches are actually biased. But this doesn't work well in these cases. But even if your branches are biased, like 75% accuracy, yes, maybe you'll get, if your profile is representative, you'll get 75%. But you're leaving on the table 25%, right? And we know that 75% is not good enough. Okay, and we already discussed this. Accuracy depends on the representativeness of the profile input set. Okay, we're going to get back to programmer-based. So there's another idea. This is actually very interesting, and I would recommend this paper. It's a fun paper to read in PLDI 93 by Tom Ball and Jim Laris. Jim Laris is at APFL. He's the dean of the computing school over there right now. He used to be at Microsoft for a long time. But basically, they wrote this paper, Branch Prediction for Free. And the idea is very nice, I think. Basically, you use program analysis. The compiler goes through the program and uses a bunch of heuristics to guess, oh, this branch is going to be taken or not taken. Not even a profile. There's no profiling involved here. You go through the program and use some heuristics. What are the heuristics? Well, one of the heuristics that they found at that time with the program they looked at was predict branch less than or equal to 0 as not taken. Why? Because negative integers may be used as error values in the program, and this is basically testing for a negative integer. And if you predict not taken, you're better than random chance. Of course, this requires somebody encoding the heuristics to have some insight into the program, or they may have done their own profiling, right? That's why this is called program analysis based. A compiler analyzes the program, says, oh, okay, BLEZ, I have this heuristic, I'm going to set that bit as not taken. Another one, loop heuristic. Predict a branch guarding a loop execution as taken. Basically, this is a branch that's really guarding the loop execution. It's not the loop branch. If X for, basically, it's protecting the loop. And the idea is to predict that to be taken, because most programs go into the loops. That's the idea. Very simple. It doesn't always work, obviously, right? But it works most of the time. This is hopefully something that works almost all the time. Basically, when you're doing comparisons, pointer or floating point comparisons, usually you predict not equal, right? If you're traversing a linked list, for example, if you were doing some comparisons with pointers, or maybe if you're doing a comparison to the key, you predict not equal because the prediction is that you're going to traverse that for a while. That's one example. I just mixed that with the key, but that's okay. Basically, if you have information about your program based on analysis, you can do intelligent prediction. So FP comparisons is if you have two floating point values, floating point value A and floating point value B. I guess you could do double over here. And then you're checking if A equal B. Not a good thing to do in real life. because floating point comparisons are not good. These are inexact values to begin with. But this happens also, and basically predict that they're not equal, and predict that this is not taken as a result. Similarly to pointer comparisons. Usually pointers don't match. Okay, the big advantage over here is this doesn't require profiling. Of course, the big downside is heuristics might not be representative or good. But and also requires compiler analysis and ISA support, but that's true for other static methods as well. Other static methods that are per branch, I should say. And this paper showed that they could get 20% misprediction rate at that time with these methods, which is really interesting, I think. I'm not sure if that's true at this point. If somebody repeats this study, I'm not sure if you will get 20%. Okay, cool. But the idea is very interesting. So what's more important, I think, here is really the key ideas and the fundamentals. And this is a very fundamental method of doing analysis. Okay, so the next one is programmer-based. Basically, as opposed to relying on a profile, rely on the programmer. That's the idea over here. You have a hint bit to set. Who's going to set it? Let the programmer set it. I just said that. So how do you do that? You put stuff in your programming language that basically enables the programmer to tell whatever is in the next layer to treat this branch as likely taken or likely not taken. And these are called, this stuff is called pragmas. Programmer can actually use these pragmas to basically qualify a branch as likely taken versus likely not taken. I'm going to show you examples of pragmas. In C, for example, there's a likely pragma that you use. But this doesn't require profiling and program analysis. That's good. But now it relies on the intuition of the programmer. And programmer may know some branches and their program better than other analysis techniques. Not always true. Your programmer needs to be very cognizant of this. Now it requires actually not only compiler and ISA support, but programming language support. Because you're at the higher level of the stack. Programmer says this. Now the compiler needs to obey this, and ISA needs to obey this also. So the programmer actually may decide this, but everybody else can ignore the programmer. That's also a possibility, right? Okay, it burdens the programmer? Yes, certainly. But some programmers are actually less burdened by these things. They tend to be in the minority. Okay, so what are the pragmas? This is an important concept. These are keywords that enable a programmer to convey hints, information to lower levels of the transformation hierarchy. These are hints. They don't necessarily need to be obeyed, but they can help performance if they're obeyed. So it's an example from C. If likely X, then execute this code. Here the programmer is indicating that this X is likely to be true. Here the programmer is indicating that error is unlikely to be true. And now the compiler can easily, if it trusts the programmer, set the bit accordingly, right? Very simple. And many other hints and optimizations can be enabled with pragmas, certainly. For example, whether a loop can be parallelized in OpenMP, you have pragma that looks like this, pragma OpenMP parallel. And the description directly taken from the OpenMP manual says this directive, or pragma, explicitly instructs the compiler to parallelize a chosen segment of code. The programmer can choose to ignore it, right? That's perfectly possible. The compiler can choose to ignore it. Okay, so that's another example of a pragma. Okay, so all previous techniques that we've discussed actually can be combined. You can have profile-based, program-based, programmer-based. Now, how would you do that is a key question. It's not clear what the answer is. But there is certainly a common disadvantage of all the three techniques that's going to motivate us to move on to other techniques. And I guess I've already given you, actually even before I've already given you this. Basically, they cannot adapt to dynamic changes in branch behavior. They have a single encoding per branch. Right? They are per branch, but they say, oh, this branch is going to be taken for its entire execution of the program. Okay. So this can be mitigated by dynamic compiler, right? For example, if you have a compiler that's jitting your program, just-in-time compilation, what it's usually doing is, on the side, it's figuring out what are the hot paths in your program. It's doing instruction scheduling and a bunch of other stuff. And it can also say, oh, okay, these branches have now changed behavior, right? And it can re-encode those hint bits somehow. It can actually do this profile-guided code positioning optimization, which basically reorders the basic blocks. It can do many, many things, including those hint bits. Now the problem is that dynamic compiler has its own overheads also. Well, what is a dynamic compiler? A compiler that generates code at runtime, right? And we've actually seen an example of this in digital circuits. The Transmeta was a company that tried to build x86 processors where they would take x86 code and they had a dynamic compiler that converted that x86 code into an internal VLIW format. They basically translated x86 to an internal ISA, instruction set architecture, and their hardware executed that internal ISA. And this compiler did many, many things internally. That's just one example of a dynamic compiler. Java is another dynamic compiler, clearly. Or Java runtime is another dynamic compiler. But this one is particularly interesting because it's taking one ISA and converting it to another ISA internally. And in the meantime, it can do instruction scheduling. It can actually do these hint bit generation, which it did, and many other things. It actually packed the instructions to schedule because x86 is not a VLIW, very long instruction word ISA. This one figured out which instructions can be executed in parallel in the same cycle and packed the instructions accordingly. Okay, that's one example of a dynamic compiler, and there are many others. And this slide is out of date. Okay, now we're here, basically. We've come to runtime. So we want to overcome the disadvantages of all of these other ones. So how do we do that? So the key idea in dynamic branch prediction is to predict branches based on dynamic information collected at runtime. Usually this refers to hardware. And there are clear advantages. Basically, you provide a prediction based on the history of the execution of the branches, as opposed to a single bit that disregards the history during runtime. Which means that it can hopefully adapt to dynamic changes in branch behavior. If you do taken 10 times and switch to not taken, you can figure that out, right? If you do taken, not taken, not taken, you can figure that out also. There's no need for static profiling, so input representativeness problem goes away, and programmer dependence also goes away. The disadvantage is more complex, you need additional hardware, and we're going to keep adding more hardware to this. So let's start with the simplest dynamic branch predictor, which is a last time predictor. And the idea is very simple. You've executed the branch once, and you know what direction it went. Use that direction as a prediction for the next time you execute that branch. Very simple idea. That's why it's called last time, right? So you get single bit per branch stored in the BTB that says what was the direction the branch went last time it was executed. And if you do that with this sort of behavior, you get 90% accuracy. Well, what does that mean? Basically, assuming that you start last time as taken, you start with the taken prediction. You basically mispredict when this changes to taken to not taken, because when you execute this one, you were going to predict it as taken because last time it was taken, but it's really not taken. So that's one misprediction over here. And then assuming that this is looping, that's the other assumption I have over here. When this instance of the branch executes, this gets mispredicted because last time it was not taken. Right? Basically, you mispredict 2 out of 20 times. If you calculate this as 20 executions, you mispredict here, you mispredict here, that's 2 out of 20. And 90% accuracy, right? 90% not bad. None of the previous methods that we discussed gets you more than 50% on this one, right? Okay, basically this always mispredicts the last iteration and the first iteration of a loop branch. That's the problem, in the steady state. Actually, in the first execution of the branch, what is your last time? You don't even know. That's the warm-up penalty, right, for this predictor. If you set it to taken somehow, you would get this correct. If you set it to not taken, you would get it not correct. That's the warm-up time. So this is a very quick to warm-up predictor, as you can see. With one execution, you warmed it up. Now, you may not be correct, but you warmed it up. Okay, so the accuracy for a loop with n iterations is n minus 2 divided by n. Clearly, as n is higher, this is very good. If an n is a million, you're almost close to 100%. Yeah. But for this one, it's not good. If n is 2, you have a problem, right? You always mispredict. So this is good for loop branches for loops with large n, number of iterations. But loop branches with small n, as I just said, you get 0% accuracy. Although this looks very, very predictable, right? But you're doing the wrong thing. You should do really opposite of last time in this case. But how do you know if you should do opposite of last time? You can figure it out, I think. So if you're a little bit smarter, you can actually add more hardware to fix this, right? You can keep track of how well you're doing, how well your branch predictor is doing, and rework the branch predictor. If you can still use the last time predictor in this case, But you could keep track of, okay, my accuracy for this branch is, I don't know, 0% so far. So maybe I should do exactly the opposite of what my branch predictor is telling me. So this sort of cases are actually easy to fix, but you need more hardware to fix those. And actually, we'll see some predictors. We're not going into a lot of detail, but existing predictors do similar stuff like this. Okay. Okay, this is one implementation of the last time predictor. Basically, this is 1 bit per branch target buffer entry. You get 1 target address per entry in the branch target buffer, and we add 1 bit saying what was the last time. What was the direction of this branch when it was executed the last time? If it's taken, and if you get a hit in the BTB, then you would actually pick the next PC from the BTB. That's very similar to what we've seen before, except the direction predictor is integrated into the BTB in this case. Right? Okay, hopefully this is obvious. So this is the state machine for last time prediction. You predict, okay, this is the last time it went taken, and you predict it taken if you're in this state. And if it's actually taken, you stay in this state. If it's actually not taken, you go to this state, and the next instance of the branch you predict not taken, and this is the state machine. It's obvious, hopefully. But we're going to build a state machine for a 2-bit predictor to solve the problem that we're having. So how do we improve the last time predictor? Basically, the problem is this. A last time predictor changes its mind very quickly. Right? If it's predicting taken, with 1 opposing outcome, if it sees the branch actually not taken, it'll say, okay, I'm going to predict not taken after this point. And same here. With 1 opposing outcome, it says, oh, I'm going to change my mind. That may not be a good idea. Basically, it switches between taken, not taken, not taken, taken too quickly, even though the branch may be mostly taken or mostly not taken. So this is like if you're trying to cool a room, for example, to 20 degrees Celsius, and your temperature is hovering around 20 degrees Celsius, and you design your air conditioning to change its mind very quickly. Like if you're 20.00001, the air conditioning goes to cooling. If it's 19.99999, the air conditioning goes to heating. And your air conditioning goes crazy between 2 modes of operation, heating and cooling, and heating and cooling, and heating and cooling, and you become extremely inefficient. Right? And people have solved this problem in control systems like that. And the solution is basically they add what's called hysteresis. They add some gap where you don't change your mind. That's the idea, basically. You don't change your mind on a single different outcome. You look for a little bit more evidence that you should really change your mind. And what is that evidence? In this case, well, maybe you should see 2 opposing outcomes. Right? And that's the idea. Very simple. In the air conditioning case, maybe you should go to a little bit higher temperature. Right? Don't change your mind within this region. Just wait until you see 20.5. Or maybe even 21. Right? Okay, so basically, how do you actually keep track of this with simple hardware? Use 2 bits to track the history of predictions for a branch instead of a single bit. This means that you can record the last 2 outcomes. You can have 2 states for taken or not taken instead of 1 state for each. And this was introduced in this other seminal paper that I didn't assign, but this is also a seminal paper. I believe this has won the ISCA Test of Time Award at some point in time, if that award was instituted. That looked at a lot of different branch prediction strategies and introduced this 2-bit predictor. This is called 2-bit counter-based predictor. It's also called bimodal predictor. Each branch is associated with a 2-bit counter. 1 more bit provides the hysteresis that we wanted. A strong prediction does not change with 1 single different outcome. That's the key idea. If you got into a state where you have a strong prediction, you need to see at least 2 opposing outcomes. But then there's also a weak prediction where you may change your mind, actually. So we'll see that in a little bit. So here, for example, if this is our loop with n iterations, and assume that we're initializing our counter to weakly taken, so you get basically 50% accuracy over here. That's the idea. If you, yeah, and you can do the calculation over here. If you actually put it to strongly taken, yeah. Actually, I'll go to the state machine over here. But basically, you get 50%. So you get better prediction accuracy as opposed to 0% if you remember. Right? If you go back over here, where is that? Okay, this was our 0%. and we had n minus 2 over n. Here I don't show that n over here, but basically accuracy for a loop with n iteration is now n minus 1 over n. You mispredict only at the end, but you don't mispredict in both sides. And here you basically keep your mind. Let's assume that you start with taken, you always predict taken. You start with not taken, you always predict not taken here. 50% accuracy. Okay, basically the better prediction accuracy is what you get, and you get more hardware cost as a burden, right? But the counter can be part of your BTB entry, that's good. So this is the state machine. This is actually, it's really a counter, a specific counter that's using saturating arithmetic, right? If the counter is actually saturated, and if you get the same outcome, you stay in that state. Saturating arithmetic is arithmetic with maximum and minimum values, so you have a maximum value 3 over here, and you have a minimum value 0, and you stay at the maximum and minimum values whenever you increment the counter with the same outcome over here. And that's the idea. So if you start, for example, in this state, you predict the branch as taken. If it's actually not taken, you go to this weakly taken state where you still predict the branch as taken. And if you see that it's actually not taken again, then only then you go to the state where you will start predicting that not taken, right? Okay, and these are the, like how the states could be labeled. Make sense? Okay, so is this good enough? That's the question we will ask again. This actually gets you 85 to 90% accuracy, this 2-bit counter based prediction, because that was a seminal paper at the time, and everybody implemented this predictor afterwards, and it got you very good accuracy, 85 90%. Is this good enough? Now we go back to this. Let's see, where is our 90%? So with 90%, with these parameters, remember we were wasting 200 additional cycles to fetch 500 instructions and 200% extra instructions. So our IPC is still very small compared to 5. So 90% is not enough, clearly. And if you're 85%, that's even worse. As you can see, our IPC is 1.25 over here, and we wasted 300% extra instructions. And if you're 80%, actually in many programs, 80% is actually still pretty good with this predictor, and your IPC is basically 1. So 5 as opposed to 1. That's why people move to other things. And basically the key idea of doing better in the next step is that we exploit last time predictability, but maybe we don't actually go back far enough. And this, we're going to talk about the seminal paper that basically introduced what we're going to talk about. And this is your assignment, basically. So this introduced 2 types of predictors. The first realization is a branch's outcome can be correlated with other branches' outcomes. Why don't we use that information to predict? This is called global branch correlation. If branch X is taken and branch Y is taken, and maybe branch Z is also taken. So now you don't look at this branch's history only, but you look at history of different branches and where they went. And we're going to motivate it. And the second realization is that a branch's outcome can be correlated with the past outcomes of the same branch. Now we are exploiting this, but we're exploiting in a last time manner. Maybe we should exploit over a longer history. Maybe we should look at last 500 outcomes of the branch, for example, or last 20 outcomes of the branch. How do we do that efficiently? That's called local correlation. And we're going to exploit both. And we're going to design branch predictors that actually have both, and existing branch predictors actually have both, and much, much more. Okay. Should we keep going or should we take a break? What do you think? This is a good natural place to take a break. Okay, let's take a break for 10 minutes, and then we'll continue. Okay, let's get started. This is where we left off, so we're going to try to do better. That's going to be our goal of life in this lecture. Actually, in all of our lectures, as you see. And the first realization is that a branch's outcome can be correlated with other branches' outcome. It's global branch correlation, and we're going to build a global branch predictor. So this is the observation. Recently executed branch outcomes and the execution path are correlated with the outcome of the next branch. I'll give you examples. I actually borrowed this from a paper that I really like that I'm going to reference later on that really analyzes why these branch predictors work. this is an example. You have this branch, if condition 1, do something. And then you see another branch, if condition 1 and condition 2, you do something. So clearly there's correlation between these two branches, right? If the first branch is not taken, then the second is also not taken. Clearly, because there's an AND over here with the same condition. Another example. This branch checks some condition. If it's true, it sets A equal to 2. And this branch checks if A is equal to 0. Obviously, there's a correlation here. If the first branch is taken, second is definitely not taken. And you could actually, these are actually different things, right? These are checking partly the same conditions. This is setting a data value based on the first condition, and this is checking that condition. So you could actually generalize these in some way. This is another example. The first branch is checking one condition, another branch checking another condition, and the last branch is checking the end of both of those conditions. And now you may empathize with this. When you program, you should be writing stuff like this also. Basically, if y and z are both taken, then x is also taken in this case. And if y and z are not taken, then x is also not taken. Clearly a Boolean function in this case. But you can become much more sophisticated. And it can be dependent on chains of dependencies, as you can see. This is actually a very famous example. There was this program called Equation to Truth Table that Equint taught. That's what it stands for. It's basically a Boolean logic. It's a tool that's used for CAD, computer-aided design. And it was a program that generates a truth table from a Boolean expression. And it had a lot of interesting stuff. And one of the branches was like this. Well, one of the set of branches was like this. I don't know what it's exactly doing, but you can take a look at the program if you're really interested. Basically, you had this B1 branch checking AA and setting AA. You had this B2 branch checking BB and setting BB. And you had this last branch comparing AA and BB. And if they're not equal, you do something. And in this case, clearly there's correlation. If B1 is not taken and B2 is not taken, then B3 is certainly taken. And this was actually the program where a lot of processors had a terrible branch prediction accuracy. This was in a very tight loop. And after global branch predictors were designed and put into the processors, this program became not so interesting anymore. Because global branch predictors are very good at predicting this branch. That's the idea. Well, this is a fun example, basically. So your benchmarks actually sometimes become not so interesting benchmarks if your hardware becomes, or if the system you design becomes very good at them, right? So you really want to move to some other benchmarks after that. There's also the benchmarking aspect of computer architecture that we've been talking about on the side. But benchmark is also interesting. You would like to ideally find the benchmark for the future, right? Because your computer architecture is going to run stuff for the future. And this was a good example at that point in time in SPEC in 1992. SPEC is Standard Performance Evaluation Corporation. Basically, it's a consortium of companies and universities and people who were basically interested in developing benchmarks. They still exist. And this was one of their benchmarks. So they develop benchmarks. Their goal is to develop forward-looking benchmarks, but a benchmark may become obsolete with an enhancement. So this is not in the benchmark suite anymore. Whereas some other benchmarks that they had in the suite in 1992 are still in the benchmark suite, I believe. There's also a 2017 version of this that I didn't really examine very carefully. Okay, so how do we capture global branch correlation? And the idea is very simple once you know what we're doing. We want to associate branch outcomes with global taken, not taken history of all branches. So we make a prediction based on the outcome of the branch the last time the same global branch history was encountered. So we keep track of the history of branches as taken, not taken. And if we see the same history again, we're going to use the same outcome. We're going to use the outcome of the branch that we saw that history previously as the prediction. So basically, you keep track of the global taken, not taken history of all branches in a register. This is called the global history register. I'm going to use that part of the board. Can you see that part of the board?
Yes.
Yes, okay, that's good. I'd prefer to use the board because the switching overhead is too much otherwise. So basically, we're going to have what's called a global history register, GHR. And let's assume that we have 16 bits over here. This is encoding the 16 previously executed branches and their taken, not taken history. This is the youngest branch. And this is the oldest branch. that we've encountered. And youngest one, let's say if it was not taken, we encode as 0. The previous youngest one was taken. So you could actually have a history that looks like this, right? Which means that the oldest ones were taken, and the next one was not taken, and the next one was taken, and the next one was not taken. So the latest branch that you've seen was not taken. And you could easily have this history basically by inserting here and shifting the register to the left. And you use the global history register to index into a table that recorded the outcome that was seen for each GHR. So use this basically as an index into a table that now has 2 to the 16 entries. Wrong way. Yeah, hopefully you can see at least some of it. 2 to the 16 entries, in this case n equals 16 bits, meaning the length of your global history register. And basically record, okay, now I see this history, and the next branch that's coming, I've just executed it, and it's basically taken. So you associate this history with a taken outcome. Taken is 1, right? That's the idea. And the next time you see this history, you consult this table, and the table says, oh, last time you saw this history, it was taken, so predicted taken this time. Next time, hopefully again, next time, hopefully again. That's the idea. So in this case, I said taken, but you can also have hysteresis here, the same idea. Who said that you can have hysteresis only in the last time predictor? You can have hysteresis whenever you see this history also. So you basically have a 2-bit counter here. Let's call this 2BC. Make sense? Basically, you associate the history of recently executed branches with a taken, not taken outcome for the next branch that's coming. This is called the global history branch predictor, and it's as simple as this basically. You have a single history for all the branches, and you have this is called a pattern history table, and this is called the global history register, as I said. So the difference here is it uses 2 levels of history. Global history register, the global history of the branches, and the history at that global history register value. Make sense? It doesn't distinguish between different branches over here. There's no program counter here, as you can see. It's purely based on this global history information. And this is exactly what I just showed you over here. The first level is the direction of the last n executed branches. Where did they go? So it's m bits. Intel Pentium Pro had 4 bits, for example. That was the first processor that had global branch prediction. The second level has a table of saturating counters for each history entry. And this is the direction the branch took the last time the same history was seen. But it could be any branch that had this history, right? There's no program counter, as you can see here. Sounds good? So we're perfectly exploiting global history correlation. This is the global history register. This is the previous branch's direction. And whenever you execute a branch, you basically shift the global history register to the left by 1 and plug in the direction of the branch over here. And inside each of these entries, you can have a 2-bit counter, you can have 1-bit counter, you can have 3-bit counter. We'll see that actually in one of the implementations. Okay, so what does this buy us? Basically, this buys us very good prediction, for example, in this example. This is from the paper that you're reading. Basically, assume that you have these 2 loops. This is iterating for 100 times, this is iterating for 3 times. This is basically this is going through the simulation of what your global register, they call it global register, it's global history register in my terminology over here. What would happen? So let's assume we're here. You're testing this outer loop branch. This is usually taken, right? You're iterating 100 times. And you get to here. Let's assume that you've gone through the loop once. This is taken 3 times. And yeah. So basically, this before we get to over here, this basically tests I over here. And this is the value of the global history register at that time. So this loop is taken 3 times, and the last time it was not taken. So this branch was executed actually 4 times internally, right? 3 times it was taken, and the last time it was not taken. That's why your global history register is 1110, and you arrive at this branch. And this branch is usually taken, so you can actually encode that taken over here. So last 4 branches actually test J, as I mentioned over here. So history is taken, 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 not taken when you reach the outer loop branch. And you predicted taken because at that history you almost always see taken. And then the next history becomes taken, taken, not taken. Basically you shift out the stop one and you shift in the prediction, which is TT and T. And where does that take us? That takes us to the first iteration of the inner loop. And in the first iteration of the inner loop, our history is taken, taken, not taken, taken, and the result is taken. And it's always taken in this case, right? Because it's a hard-coded loop. And then if you actually keep doing the simulation, when you go to the next iteration of this, you shift this out, you shift it in, so you get to 1, 0, 1, 1, taken, not taken, 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 and the result is taken. And when you get to here, this is the history, and the result is not taken. So you basically predict all the branches correctly once the predictor is warmed up, except for the exit from the outer loop. Everything else is predicted correctly once the predictor is warmed up. Make sense? And you can actually do the simulation for yourself. And this paper actually beautifully describes these predictors. So this is one of the best papers that describes these really well, even though it's a technical report. Okay, so that's the idea. This was actually implemented, this influenced industry right away. This is not the paper that introduced this particular idea, but this explains it very well. The paper that I mentioned that you also are supposed to read, that is the one that introduced the idea. And it was implemented in Intel Pentium Pro circa 1995, 96. It had a 2-level global branch predictor, what I just showed you, except its history was, global history register was not 16 bits, it was 4 bits at the time. Now we're beyond 16 bits actually, but this was 1995. And it had multiple pattern history tables, basically 2-bit counters. It was a little bit different from what I showed over here, but not that much. Conceptually it's the same. Conceptually it's exactly the same actually, but they did make use of, actually let me build it very quickly, it's easier than going through here. So you basically have 4 bits, which means that you have 16 entries over here. But they did have multiple of these pattern history tables. Pattern history table 0, pattern history table 1, I guess pattern history table 2, and pattern history table 3. And what they did was they actually accessed them in parallel using the history register, got a prediction, and basically had a mux to select the one that they wanted. And how did they control the mux? Now they use the program counter. Basically they picked 2 bits out of the program counter, and that was the control of this mux over here. Now you're using global history. It's a global branch predictor, but you're kind of distinguishing between different sets of branches. What are the sets of branches? These are the set of branches that have 0, 0 in their addresses over here, 0, 1 over here, 1, 0 over here, 1, 1 over here. Why? Now we are basically trying to distinguish between different sets of branches, right? You're adding, because if you have a single table over here, there might be a lot of interference in that table. Now you actually can say if one branch that has address 0, 0 is conflicting badly with another branch that has 1, 1, you're putting them into separate tables. That sounds good, right? So we also already saw caching and conflict reduction. This is one benefit of conflict reduction. The other benefit is it's giving you context information. Maybe this history is always giving you some outcome with this particular branch, whereas it's giving you some other outcome with some other branch, right? That's the idea. Because there is no single correlation. This is global correlation, and this is what happens for that particular branch. And if you actually had a purely global table, single pattern history table, you're really not taking into account anything about the branch that you're predicting. Now you're taking into account something about the branch you're predicting, how that history behaves for that particular branch. So this kind of gives you a more general view of predictors. So this is actually called a global predictor still, but the pattern history tables are like per set of branches. So it's not per branch. It's not single also. It's not completely global also. It's really for per set of branches. You have a choice over here. It could be global, a single table for all branches. It could be per set of branches, or it could be per branch. Per branch is a bit harder because you may have many, many branches, right? It's very hard to do that. So usually people build either this one, a single table, or a per set of branches. Okay, now I'm giving you the Intel Pentium Pro predictor. Does that make sense? Okay, after that, there are many, many predictors. And we're going to see some more of them. Okay, so this is the paper that I mentioned. So why does this work? There's actually this paper that discusses, like, why do these predictors actually work? And they do a lot of analysis, which I'm not going to go into the details of. But one of the things that they show is, these are several code patterns why these predictors work really well. But they also do analysis, I think, going up to 512 previous branches. And they say, actually, if you're predicting this branch, only three, on average, only 3 past branches' directions really matter. If you somehow magically knew those 3 branches, you could predict this branch very accurately. Now the problem is, those 3 branches differ for the different branches that you're predicting. For this branch, it could be the branch that's at 512 bit in the history, 512 branches earlier, and 100 branches earlier, and 5 branches earlier. For this other branch, it could be a completely different set of 3 branches. And also, it's not 3. For some branches, it's only 1 branch that matters, right? If this branch is taken, this other branch is going to be not taken. So there's a lot of very interesting analysis in this paper that I'm not going to go into. But this provides a lot of insight that enabled the building of other predictors. It's a complete analysis paper. Okay, so how do we improve global branch predictor accuracy? As I said, so this one, for example, Intel Pentium Pro actually improved the global branch prediction accuracy by adding more context and with the PC, and also reducing interference. So one idea is adding more context information to the global branch predictor to take into account which branch is being predicted. One way of adding the context is like the way Intel Pentium Pro did. Another way of adding the context is introduced in this paper, in this combined branch predictor paper, which was also popular. Basically, don't use just the global history register, but hash it with the branch PC. Very simple idea. This is the branch PC. This is the global history register. The same thing over here. Just do an XOR. Now this has multiple benefits. One is you take into account the branch information, not just the history information. More context information. It also gives you better utilization of a single pattern history table. And you don't need to add multiple pattern history tables like Intel Pentium Pro did over here. Of course, there are benefits and upsides to adding and not adding multiple pattern history tables, and you can think about those. But this better utilizes your pattern history table. Make sense? Okay, cool. Of course, what is the downside? It's increase your access latency, but that's going to be true of everything that we're going to examine going forward, I think. So this one also increases your access latency because you have a mux, right, to select between different outcomes of the pattern history tables. Okay, so basically this was our 1-level branch predictor. I'm going to go through this very quickly. So we added 2 levels. So how do we do that? Basically we had this global history register, yes, and used that to index our direction predictor, and everything else remained the same. Now G-share is basically this, global history register XORed with the program counter. And we still have a single pattern history register in our direction predictor. So people actually realize that this single global pattern history table has a lot of interference in it. So we actually talked about cache conflicts, right, earlier on. Some of the solutions that we're going to develop will be similar to cache conflict reduction over here. You will see that. G-share is actually doing, in addition to adding context information, it's randomizing the index into your pattern history table. So it's actually reducing conflicts. But let's talk about this interference issue a little bit more, because there are some interesting ideas that you can use over here. So sharing the pattern history tables between histories and branches leads to interference, clearly. So maybe I should pull this up because I keep pointing to it. It was probably a sweet spot here. Basically, if you have a single pattern history table over here, if you share it across branches and global histories, you can have interference. Basically, different branches map to the same pattern history table entry, a single entry over here, or a single entry over here. and modify it. And interference actually can be positive, negative, or neutral. If both of the branches are behaving similarly, they can have positive interference. They can enable one branch is, for example, figuring out the mispredictions earlier and changing the history over here, and the other branch is not predicted correctly. That's positive interference, right? Branch A and branch B, basically they may index into the same counter. That's the interference here. But it could be negative, or it could be neutral. They don't affect each other that much, even though they update the same counter. But the worst part is when they are negatively interfering with each other. They map to the same entry, and this branch wants to be taken when this other branch wants to be not taken. Right? That's the real direction, but because they map to the same entry, they're conflicting. One branch is pushing the counters to be taken, and the other branch is pulling the counters to be not taken. As a result, both may be mispredicted all the time. And that's a problem with interference, right? And this is only 2 branches, right? You could actually have 100 branches mapping into the same entry, because it's just a mapping function. Especially if you have a 4-bit global history register, you have 16 entries over here, and you may be executing 100, I don't know, tens of thousands of branches actually in your program. People have shown that, for example, IBM builds these big mainframe servers, and those are the servers that execute a lot of code, financial code. And it turns out in a lot of that code, there are lots of branches. And if you look at IBM's processors, the Z series, their target buffers are, I don't want to, they're at least 16,000 entries. So those were the big buffers. I believe right now they actually have maybe 64,000. Don't quote me on it. You can actually look at it. But they actually have a large branch working set. And if this is only 16 entries, then you have a lot of interference over here. That's one downside of having small pattern history tables. So you don't want to have small ones. So current ones actually are big. But can we actually solve this problem of interference? Can we actually eliminate this interference somehow? So one way of eliminating clearly is dedicate a PHT, pattern history table, per branch. But per branch, if you have 60,000 branches, this is not feasible clearly. So too much hardware cost. So basically, you can dedicate a PHT per sets of branches like Pentium Pro did, and that's not a bad solution. But can we still do better within a single table? How else can you eliminate or reduce interference? So we're going to talk about some ideas. One is increasing the size of the PHT in vertical or horizontal dimensions. We're going to ignore that for now. The other is filtering branches. And this is a nice idea. Predict highly biased branches separately so that they do not consume PHT entries, pattern history table entries. This is kind of obvious. Maybe you could use the BTB or the static predictor for that. Hashing and index randomization, G-share. We're going to see the G-skew also. It's going to be very similar to skewed associative caches. They'll look by the same person. And we're going to see a kind of an interesting idea, agree prediction. Let's start with the biased branches. This is a very simple idea. People actually, after they built a lot of branch predictors, they observed that many of the branches are biased. Meaning they go 99% taken or 99% not taken. Pick your threshold. And these biased branches are actually much more easily predictable with some other predictor, right? You don't need to consume valuable global history register and pattern history table resources for them. So somehow figure them out. Basically, the problem is they pollute the branch prediction structures. They make the prediction of other, perhaps harder to predict branches much more difficult by causing interference in branch prediction tables and history registers. And you don't really need the sophisticated machinery to predict them. So the solution is somehow detect such biased branches and predict them with a simpler predictor. It could be last time. It could be profile-based static. It could be, basically something that's separate from the predictor you have. Then the key question is how you detect such biased branches. You need to have some counters for this, and you need to have some additional metadata in your BTB. So there's usually a cost associated with doing this, but many systems actually do this. They detect biased branches, and they use a much simpler predictor for this purpose. And this was introduced in this paper in Micro in 1994. That's all I'm going to say about it. This is hopefully an obvious idea, right? I think the fundamental principle is you have this valuable structure that provides you some prediction. Don't waste it on things that you can easily predict. Right? Just use it whenever you really need it. Right? That's the fundamental principle. And this principle applies for everything, right? If you have a valuable resource, don't waste it. Okay, so G-share, we've already seen this. Basically, randomize the indexing function into the pattern history table such that the probability of 2 branches mapping to the same entry reduces. You could do it in multiple ways. One way of doing it is G-share, as motivated in this paper. You basically hash the global history register with the branch PC. Now, G-share is not purely for interference from this perspective, right? If you really want to just minimize interference, you take the branch address and go through a hashing function. You don't extort with some other contextual information. So G-share is actually based on two things. It's not just trying to reduce interference, but it's also trying to improve prediction accuracy at a given branch history register by adding more context information. So basically, these are the two benefits of it. Well, the downside we've already seen. The downside you cannot get away from. We're going to try increase access latency, but access latency is really, really important over here. Okay, so I'm going to give you another idea that I really like. This is actually a kind of an out-of-the-box idea, I think. Basically, it was introduced in this paper. The idea is very simple again. Usually good ideas are simple. It's called agree prediction. Agree prediction says you somehow figure out a bias bit associated with a branch in the BTB. Ideally, that's the most likely outcome for the branch. So somebody figures this out. It could be the compiler. It could be the programmer. It could be anyone, basically. It could be dynamic also. You could change it potentially. But you would really like to be accurate in this. And remember, most branches are biased. 90%, 99% taken, or 90%, 99% not taken. Good. Now, we're going to use the pattern history table for a different purpose. Here we have the bias bits. Everything else is the same, the global history register. But pattern history table, what we're going to encode here is whether or not the prediction or the counter agrees with the bias bit or disagrees with it. Remember, previously we were encoding whether or not the prediction is taken or not taken, right? At that history, should we predict taken or not taken? That was what we were doing. Now, we've kind of eliminated that. We say, at that history, do we agree with the bias bit or do we disagree with the bias bit? Sounds good, right? So far, so good. That's the prediction. Do we agree with the bias bit or do we disagree with the bias bit for this branch? And this reduces negative interference for the reason that I'm going to show you. Because if all of the branches are biased, they will keep on agreeing. Right. If the bias bit is correctly set, and most of the branches are biased, you will increase the positive interference. You will reduce the negative interference because whenever you do the prediction, you're going to agree, assuming your bias bits are correct. And you're unlikely to disagree. That's the idea. But of course, this requires determining the bias bits. So let's take a look at an example. Assume two branches have taken rates of 85% and 15%. Assume they conflict in the PHT, pattern history table. They go to the same counter. And let's compute the probability that that same counter, they have the opposite outcomes, basically. So in the baseline predictor, this is the probability of misprediction. Basically, probability that B1 is taken and B2 is not taken. They're mapping to the same place. And one of them is saying taken and the other is saying not taken. So as a result, they're basically destroying each other's prediction. Or it should be the other way around. Probability that B1 is not taken and B2 is taken. I'm, of course, simplifying this because we're not taking into account the hysteresis and all of that stuff. But think about a single bit. And if you do this calculation with these rates, both of them have taken rates of 85%. Well, one of them has a taken rate of 85% and the other has a taken rate of 15%. They're directly opposite of each other. The misprediction rate would be 74.5%. Right? This is the probability of how often they have opposing outcomes in the baseline predictor that tries to predict, should I predict taken or not taken? Does that make sense? Hopefully this is clear. Everybody agrees with this? Okay? Basically, probability that branch 1 is taken is 85%. Probability that branch 2 is not taken is 85%. That's one case of misprediction because they're going to go against each other in this case. And the probability of B1 not being taken is 15%, and B2 being taken is 15%. That's another case where they're going to go against each other. We're not counting, of course, probability of B1 taken and B2 taken, because then they're not going to go against each other, right? The predictor is going to be fine with that. But the predictor cannot handle these cases. So 74.5%, you get mispredictions if they're mapped to the same location in the pattern history table. Now, what does the agree predictor says? Agree predictor says, set this branch B1's bias bit to taken, and B2's bias bit to not taken. And whenever you're doing the prediction, predict whether you agree or disagree with the bias bit. Right? So this branch will agree with the taken, which is its bias bit, and this branch will agree 85% of the time. It will agree with the taken. This branch will agree 85% of the time with the not taken. And agree predictor's probability of misprediction, in that case, will be this. Probability that B1 agrees with its bias bit and B2 disagrees, plus probability that B1 disagrees with the bias bit and B2 agrees. And if you do this calculation, you just change the numbers. B1 agrees with this bias bit 85% of the time, B2 disagrees with the bias bit 15% of the time, because you set the bias bits correctly. Remember, B2's bias bit is not taken. And B1 disagrees with its bias bit 15% of the time, and B2 agrees with its bias bit 85% of its time. As a result, you get 25.5% misprediction rate. I think it's a very clever idea. By using one level of indirection, which is the bias bits that you hopefully set correctly, you get rid of a lot of mispredictions. This works because most branches are biased, not 50% taken, and most branches are actually 80%, 90% taken or not taken. Of course, it doesn't work if branches are not biased, and it doesn't work, actually it may become worse, if you don't correctly set your bias bits. Okay, that's the idea. So if you're interested, you can read the paper. It's a beautiful paper. Okay, how else? So this is directly trying to reduce the interference, right? G-share, remember, by XORing the bits with the global history register with the PC, it's actually adding more context information. Here, we're not really adding more context information to the predictor. We're really trying to get rid of the interference. This is another idea. If you remember this skewed associative caches, you're going to remember something like this. Basically, the idea is a G-skew predictor, and you probably remember this name also, says Nick. The idea is to have multiple pattern history tables, and each one is indexed with a different type of hash function. And the final prediction is a majority vote over here. Now, if you happen to badly interfere with some other branch over here, and this prediction is not good, hopefully these two will get that right for that branch. That's the idea. Basically, distribute the interference patterns in a more randomized way across different PhDs, and interfering patterns are less likely in different PhDs at the same time. And if basically, as I said, if two of your PhDs are don't have bad interference for the branch that you're trying to predict, then hopefully you've eliminated that interference in one of the PhDs. And you could, of course, take this idea further, have a bigger majority vote across many PhDs. So this is actually interesting. We're going to build up to some other predictors with this. And here, if you look over here, the indexing function is the only thing that's different. Branch address and global BHR, they're kind of the same. But you may actually have different lengths of this history register also, as we will get to in a little bit. Okay, does that sound good? It's similar to skewed associative caches in some way. Okay, of course, now we have more complexity. I mean, everything we've said adds more complexity to the system. Bias bits in the agree predictor, you need more complexity. Here, you need complexity due to multiple PhDs and hash functions, and access latency also increases. So people have actually developed many, many other ideas to reduce interference in the pattern history tables. I'm going to very quickly go over some of them. There are many, many, some alive, mostly dead papers that are written that try to reduce this. These are some interesting ideas. Basically, you separate the pattern history tables for mostly taken and mostly not taken branches. And it's kind of a similar idea, right? You reduce the negative aliens. If some branches are mostly taken, handle them here. If some branches are mostly not taken, handle them here. That reduces the negative interference a lot. There are similarities with the agree prediction here. Yet another great scheme predictor, YAGS predictor. And you can see how many predictors that people have gone through over time. This basically uses a small tag cache to predict branches that have experienced interference. Basically, if somehow you predict that you mispredicted a branch because of interference, you try to not mispredict them again. Kind of like a victim cache at some level. Right? Okay, you can read that paper if you're interested. And there's also this is a very interesting paper that actually does a lot of maybe black magic, hashing, trying to determine which address bits to use for the alpha EV8 branch predictor. Alpha 21 to 464 was the latest processor that was designed by essentially Compaq or Digital Equipment Corporation that never saw the light of day because of various commercial issues. But it was a very aggressive design, and they wanted to design the best branch predictor. And Andres Sesnek worked with them actually, and he wrote this paper that goes into a lot of nitty-gritty detail on how they made some of the design choices for this conditional branch prediction. If you're really interested in branch prediction, you should take a look at it. But basically, there are a lot of techniques to reduce interference in that prediction with a given budget, of course. If your budget is unlimited, then it's relatively easy, but your budget is always limited, as we discussed earlier. Okay, so we're done with the global part, the first realization. And I've given you a summary of a lot of years' work. Let's go into the realization 2, which is also interesting and which is also employed in existing processors. Basically, the key realization is that a branch's outcome can be correlated with past outcomes of the same branch, in addition to the outcome of the branch last time it was executed. So 2-bit counters do this somewhat, but we want to actually do even longer histories. So let me give you an example. This is also from the paper that I assigned. If you look over here, I'm going to read this actually. If the loop test is done at the end of the body, the corresponding branch will execute the pattern 1110 to the n, where 1 and 0 represent taken and not taken respectively, and n is the number of times the loop is executed. Clearly, if we knew the direction this branch had gone on the previous 3 executions, then we could always be able to predict the next branch direction correctly, and with that correctly at the end. And that's the idea, basically. So these things work for loop branches, not only for loop branches, but loop branches are a good example for this. You just need longer histories for this. So how do you get that? Basically, this is an example. This is loop closing branches history, how many times you execute this branch. And you see the history over here. And to predict the loop branch perfectly, we want to identify the last iteration of the loop. And by having a separate pattern history table entry for each local history, we can distinguish different loop iterations of a loop. This works for short loops. You can read the paper for more detail over here. So how do you capture this? And the idea is very simple now. As opposed to having a single register that looks like this, that's global, that's shared across all branches, well, why don't you have a per branch register? For each branch, you have a 4-bit history. Associate the predicted outcome of a branch with the taken, not taken history of the same branch. Local correlation. Okay, and we've already said this. Basically, to make a prediction based on the outcome of the branch, the last time the same local branch history was encountered. If this local history of this particular PC was 1110 and the outcome was taken, next time you see 1110 for that loop, predicted taken. Very simple. I mean, it's a natural extension of global correlation. They're introduced in the same paper as a result of this. It's called the local history or local branch predictor. It uses 2 levels of history again. Basically, you have a per branch history register, not a global one, but a per branch. And you also store the history at that history register value. Basically, you still have 2-bit counters, or you could have 3-bit, or you could have 1-bit, right? Because you may actually have the same behavior, like not interference, but hysteresis behavior, as we've seen before. So that's why it's 2 levels of history. Okay, this is the example. We just had local history registers. This is branch A, branch B, branch C, branch D, branch F. So this is not going to be feasible, as you can imagine, for all branches. And each of them have a local history. And you select the history register based on the program counter of the branch, and you can pick m bits. The second level is a table of saturating counters for each history entry. Now, what does this mean? If this is global, you may argue that makes or that does or doesn't make sense, but let's assume that that's global. You basically take this history and index, and the pattern history table gives you what you should predict. The direction the branch took the last time the same history was seen. Of course, it doesn't make sense for this to be global that much, right? Because now you're having a per branch global history register, but shared or global pattern history table across all branches, a single pattern history table. It does exist, actually. It's possible to build that, and we're going to develop a taxonomy of branch predictors, but it makes more sense for this to be per set. Does that make sense? Because you're having per branch information over here, and you may be destroying it over here if you have a single global table. Okay, and we've seen that already. So basically, this is two-level local history branch predictor. You take the program counter. There's no global history here. This is purely local. You take the program counter, figure out the history at that program counter, and use that to index into a direction predictor that gives you the taken or not taken. And hence the two levels, one level, second level. And which directions earlier instances of this branch went is your history in this case. Okay, so this is the taxonomy that I kind of promised you. This is another paper that won the ISCA Test of Time Award, actually in 2007, I think. Basically, in this case, so these are different taxonomies, and these are three examples of this. So the branch history register, I call it the global history register over here, but it doesn't have to be global. That history register over here can be global, maybe meaning one register for all branches, or it could be per set of branches, multiple registers, but different sets of branches based on the PC mapped to different registers, or it could be per branch in the extreme case. You have one register for every branch. And we've seen this one clearly, and we've seen also this one. Now, the counters, let's go to the counters later. The pattern history table itself can be global, per set of branches, or per branch. This is the global. This is the per address, or per branch, as they call it. So for every single branch, you have one of these pattern history tables. And on top of this, the counters themselves can be adaptive or static. Adaptive meaning you have a 2-bit counter that's dynamically changed, or static meaning maybe the compiler populates this. Who knows how? But you could potentially populate this table at compile time. Let's not get into that. You can read this paper if you're interested in that. That usually doesn't perform very well. And it's also a lot of complexity in the compiler. Okay, so these are examples. This is the global predictor. It's called, BHR is global in this case. Pattern history table counters are adaptive. They're not static. And PHT is also global. This is exactly what I had here for the global, but not this one. This is the Pentium Pro. If you have only one PHT over here, that's the same as here. This is actually GAS, right? Global, adaptive, and per set. And this is another one, per branch, adaptive, and this is global. This is what I said earlier. That doesn't make sense that much, but it's possible to build, and we're going to see an example. And this is PAP. Actually, this is per address, adaptive, and per address over here also. Usually, per address is hard because you need to ensure that there's a history for every single branch. Usually, these are set-based, meaning you use some of the bits in the program counter, maybe a hash of it, to determine which history register to use. So usually more implementable form of local prediction is really SAS as opposed to this per address based. But you can read this paper for the taxonomy and evaluation of all of these different predictors with the workloads of their time. Okay, it's a very insightful paper actually. Okay, so now we're done with some of this, but not all of it. We always want to do better. This local and global branch predictor, is it good enough? People quickly realize that it's not. Predictability of branches varies. And some branches are more predictable using local history, and some are more predictable using global history, just for the reasons that we've discussed, right? If you look at the code examples, they're very different. A loop branch with long history requirements is not easy to predict with a global predictor. Because you really need local history there, but the other stuff that comes in the way, all of the other branches that populate the global history register actually interfere with you. That's another form of interference. So for others, a simple 2-bit counter is enough. Yet for others, a single bit is enough, right? And some others you don't need to, yeah. Okay, so basically the observation is that there's heterogeneity in the predictability behavior of the branches. And whenever you have heterogeneity, the first idea that should come to mind is, why don't we have heterogeneous predictors? There's no one-size-fits-all branch prediction algorithm for all branches. So let's exploit that heterogeneity by designing heterogeneous branch predictors. And the idea is simple. It's in the other paper that you're reading. Use more than one type of predictor or multiple algorithms and select the best prediction. For example, hybrid of 2-bit counters and a global predictor. Advantages, you get better accuracy. Different predictors are better for different branches, but of course you need to have a selector that's intelligent, that needs to pick the right predictor. Assume that for now. And the other advantage, as I said earlier, reduces the warm-up time. Faster warm-up predictor is used until the slower warm-up predictor warms up. And actually, some of these predictors that we've discussed, if you have very long histories, or if you have many, many branches, then it may become it may take a long time to warm up these predictors. If you assume that you have a 16-bit history, when do you consider the predictor to be warmed up? Right? Maybe some entries are warmed up in the predictor, but some entries are not warmed up yet. Right? So this is an issue actually with these large predictors. You can rely on some other predictor until a bigger predictor warms up. So disadvantages, of course, you need a meta predictor, as I said, or a selector. Now you have even longer access latency. As I said, we're going to increase the access latency for getting more accuracy. And this is a real example. It's actually beautifully described in this paper, 21264, Alpha 21264 microprocessor. They basically had, as you see, minimum branch penalty of 7 cycles, but typically it was 11 cycles because there was out-of-order execution and branches waited in the scheduling buffers for some time. As you see, their BTB was really part of iCache. 48K bits of target addresses are stored in the iCache. And there are other issues that we are not touching upon, but they can be handled. For example, predictor tables are reset in a context switch. What happens on a context switch? You've warmed up all these predictors, and some other application is running right now. What do? One way is actually resetting them so that you start from a known state, as opposed to using the predictions that was using the state of the branch predictor as it was set by a previous program, right? There could be interesting things. Actually, there are some interesting research areas over here because some of the threads that you may have in the system are very short-lived. Maybe they execute 100 instructions, 500 instructions, and they're done. How do you do branch prediction for them so that you can reduce the latency? And if all of your threads are like that, how does your branch predictor behave? I think that's an interesting area, for example. But we're not going to get into that. But that was not their design point also. Okay, so what's the point over here? This is called a tournament predictor. It's a hybrid predictor. As you can see, there's a global prediction, and then there's a local prediction. And final prediction is selected by what they call choice predict. And let's take a look at each of these. Global prediction is very similar to what I just showed you over here without the additional pattern history tables. It's a GAG, basically. You have 12 bits of global history, and you have a 2-bit counters, and that gives you a global prediction. Local predictor is somewhat similar to what I showed you. Basically, you have not a per address, but per set local history table. Each local history is 10 bits, and you have 1024 of these. And then with those 10 bits of history, you index into this local predictor that's actually G, global in this case. Meaning what they had was SAG in the terminology that we just discussed. This is global. But they actually increased this hysteresis to 3 bits. So they have a 3-bit counter in this case. So this is based on their design choice and evaluation, which they don't go into a lot of detail clearly. And the final prediction is based on a choice predictor that makes its choice based on, assuming this is accurate, just a global history. May or may not be accurate, I don't know. It also depends on how they update these predictors, which they don't go into detail. Right? There are update policies for each predictor, and there's update policy for the choice predictor, clearly, in this case. But assuming this is correct, this means that if at this global history, one predictor is doing much better than the other, choose that predictor. Right? If both of them are doing well, probably you can choose either one. And that's the idea. And this is actually the basis of many other predictors. Clearly this was there in 21264, but existing predictors have this sort of heterogeneity in them. Okay, so are we done with it? So these hybrid branch predictors actually work really well. For example, you can get 90 to 97% prediction accuracy on average. But some difficult workloads still suffer. GCC is a very good example. It's one of the worst workloads for branch prediction, but there are many, many others. For example, I think this is from this paper. Maximum IPC with tournament prediction is 9, whereas maximum IPC with perfect prediction is 35, which means that branch prediction is still limiting you, of course, with some machine assumptions. It's always good to these ideal studies. If I had a perfect predictor, what would my IPC be? And this is another example, actually. This is from another paper, which we may cover later on, which shows that it's not just the branch predictor. Actually, branch predictor and caches go hand in hand. If you make both of them perfect, you get a huge boost in performance. If you have one of them perfect, you get some boost. But the real performance you unleash by making both of them perfect. And it makes sense, right? If you're stalled by the cache, if you make your branch predictor perfect, basically your bottleneck, some other bottleneck still remains. But this is a paper that I would recommend. So here, they examine real branch predictor, real caches for different workloads. I think this is spec 92 for different workloads. I'm pausing because spec 92, okay, maybe it's not spec 92. Anyway, doesn't matter. It's some sort of spec workload. So this is the instructions per cycle that we would get in a 16-wide machine with some assumptions. So it's relatively low for a 16-wide machine. If you make the caches perfect, you gain some benefit. Their memory latencies were not as high as today. And the workloads were not very intensive. So take this with a grain of salt. If you make the predictors perfect with real caches, okay, some applications benefit a lot. These are not very memory bound, but some applications do not benefit a lot over here, especially the memory bound ones. But if you make both of them perfect, then you actually get a huge gain. Relatively close to 16 with some assumptions. And I don't know the assumptions off the top of my head, so you can look at the paper. So the takeaway is there's heterogeneity in the workloads, clearly. Some of them benefit a lot from caches. Some of them benefit a lot from just pure perfect branch prediction. I think this was compression, for example. But the biggest benefit comes from making both of them perfect. Okay, and we want both of them perfect, right? We always want the best. So we'll talk about some other branch predictor types now. We're going to make it even better. And I'm going to take a break once we actually finish the state of the art today. So bear with me for a while. So people realize loop branches can be potentially detected and predicted separately. We're going to offload some of the tasks to specialized structures. And loop iteration count detector and predictor. So there are machines that actually try to detect how many, basically you figure out branches backwards, first of all, and you allocate some structure to it, let's say a location, and you figure out how many times did it iterate. And the next time you get to that branch, you start counting down. How many times did I see this branch iterate? And you basically predict based on that last iteration count. And this works well with loops with small number of iterations where the iteration count is predictable. And this is first used, as far as I know, in Intel Pentium M, the original Intel Core architecture. Okay, we're going to see an example of this. We're going to talk about perceptrons. This is basically one of the successful applications of machine learning to computer architecture that exists in some systems. Basically, the idea is to learn the direction correlations between individual branches and assign weight to correlations and adjust those weights dynamically. Because those are the correlations. We're going to look into this in a little bit more detail. And this is another predictor. This is actually the basis of the state of the art. These two, but this one is a little bit more accurate, it turns out. And the idea is to use different tables with different history lengths and a lot of black magic on top of that. Nothing is black magic, of course, but a lot of optimization techniques. Okay, let's take a look at this. This is Intel Pentium M predictors. This is basically the loop detector logic, according to them. They call the advanced branch prediction. And there's a paper. Intel used to write these papers. Actually, IBM used to write these papers also, where they actually describe their processors nicely. IBM's papers were actually much more detailed. And this is one of those examples, one of the latest ones. I'm not sure if Intel is writing that detailed papers anymore, which would be nice, actually, if people write these papers. But this is an example. They don't give out a lot of detail. But they do give out enough detail that there is a branch predictor that detects loops. And this is similar to what I just described, right? You basically figure out a branch is a loop branch, meaning a backward branch. Count how many times it iterates the first time it iterates, how many times the loop was executed. Set that to the limit. And basically, the next time you encounter this branch, start counting. If you reach the limit, set the prediction to be not taken. That's the idea. And they also had an indirect branch predictor, which we're going to talk about a little bit later. So that's a completely different predictor. So this shows that actually some branches are much more specialized, and you can predict them more easily. So let's talk about, now the perceptron is not specialized. It's a more of a general purpose prediction mechanism, again, for all branches. And the idea over here is simple. Basically, we want to use a perceptron, one of the simplest form of machine learning, to actually predict these branches. And they found out that this is a good application of the perceptron in an important context. They meaning Okay, that paper is not referenced here. But perceptron was actually introduced in the 1960s. And it's basically a simplified model of a biological neuron. It's also a simple binary classifier. What it does is it maps an input vector x to a 0 or a 1. Input is vector x. We're going to later apply it to branch prediction. And it learns a linear function, if one exists, of how each element of the vector affects the output. This is stored in an internal weight vector. So the weights are the correlations of how each of the elements of the vector affects the output. You have one weight for each element. And output is something like this, basically. You multiply the weight with x, vector multiplication, and you add a bias. If that's greater than 0, then you predict that it's 1. Otherwise, you predict that it's 0, basically. In the branch prediction context, which is more important here, vector x is the branch history register bits. Those bits over here. We're going to build a global perceptron predictor here. Those are the bits. And output is the prediction for the current branch. And we're going to learn the weight importance of each bit. And for example, if this was taken, it's going to, and it's correlated with the current branch, its weight is going to be a positive, large positive value. If for example, this one, so assume that the branch is going to be taken, and this bit over here is the first bit, let's say, maybe I should go over here, and the first bit over here is positively correlated. When this is 1, the outcome should be 1, most likely. That's the correlation. Then this will have a large positive weight. If this one, if this bit is negatively correlated with the outcome of the current branch, it will have a large negative weight. And you will learn these weights during the execution of the program, such that your output is going to be this function. That's the idea. And this is the perceptron. I think pictorially you can think of this way. Basically, this is the output function. And these are the different bits of the global history register. And these are the weights that we've learned over time. And this is the natural bias of the branch. You also learn the bias of the branch. And this is the prediction that we have. And the idea, as I said, is use this structure to learn the correlations between the branch history register bits and the branch outcome. Basically, we are learning a target Boolean function of n inputs. And let's go through this relatively quickly. Each branch is associated with a perceptron. So you have a perceptron with the weight bits over here. Each perceptron contains a set of weights, wi over here, plus the bias. Each weight corresponds to a bit in the GHR, just like we said. And how much the bit is correlated with this is not a full sentence. How much the bit is, the weights encode how much the bit is correlated with the direction of the branch. Positive correlation leads to a large positive weight over time, and negative correlation leads to a large negative weight. That's the idea. And the prediction is, this is one way of building it. You express the global history register bits as 1, encoding taken, and -1, encoding not taken. And you basically take the dot product of the global history register and the weights. And if the output is greater than 0, you predict it taken. If the output is less than 0, you predict it not taken. So it's very simple. And you set the bias accordingly. Bias is actually to help with the bias. But you can read the paper for more detail of this. And this is the paper that introduced the idea for the first time. So if you want to really look at this over here, you basically take the branch address. You have a table of perceptrons, essentially the weights. This is a local one, basically based on the branch address over here, but you could make it global as well, which is interesting. And you basically select the perceptron over here and compute this y using the history register. It's basically a dot product of the history register and the perceptron plus the bias. And you do the prediction. And to be able to do the training, you take into account the branch outcome, whatever you computed before, and the selected perceptron, and adjust the weights. And you can see that you basically adjust the weights up or down based on the correlations that you find out during execution. Right? So, okay, prediction, bias of branch independent of the history, as you can see, and dot product of GHR and perceptron weights. And output is compared to 0, as we've discussed. And training is, you can read the paper, it's kind of obvious once you actually know how it works. Okay, does that sound good? It's very simple, clearly. Perceptron is not very sophisticated, but it works actually really well. So basically the advantage is it's a more sophisticated learning mechanism. Clearly now you're trying to learn these correlations and it gives you a better accuracy. Disadvantage is actually it's hard to implement. You basically need an adder tree to compute the perceptron output, right? It's basically this. It's basically a dot product and addition for prediction. And training also is complex as well, but training maybe could be off the critical path. That's one disadvantage. Although people have written papers and actually they've built these things, they've overcome some of those disadvantages. But if you really want to have a lot of history length, this is not easy to scale. You need to pipeline the predictor, basically. You need to start doing these computations much earlier. Don't start it at this stage, basically. Whenever you fetch the branch, it's too late. You need to actually get these predictions with a look ahead much earlier. Okay, so of course another disadvantage is basically the disadvantage of perceptron. It can learn only linearly separable functions. Basically, it cannot learn XOR type correlation between two history bits and the branch outcome. But you can read perceptrons for that. Any questions? Yes?
So there was this graph before that was like the real branch, real cache.
Yes, that's cool.
So then that was from 1999. Like, what does it look like today?
Oh, that's a good question. I like the question. Maybe you can do the same study, Ed. I agree. I think this actually, these are actually really good studies to do over time. This is from 1999. I actually did this study in my thesis, but I don't remember. I think basically I do remember the outcome. The outcome is memory latencies have become much longer. Branch predictors have become better. As a result, memory is a bigger component. But this also depends on what system you're trying to design, right? So the only thing I would say is perhaps perfect caches have become a lot more important today.
Is the difference so big still? Like,
in terms of like perfect and not perfect?
Yeah, exactly.
Oh yeah, the difference is very big still. So I can definitely say that, say yes to that. Even with memory, the difference is actually very big. And this is a 16 wide pipeline. So if you want to build a 16 wide pipeline, you really want to keep everything full. If you do the study with a 3 wide maximum IPC, then you won't see that big of a difference. But if you do it with 16, you will see that big of a difference. But these are really good studies to do actually in simulation. And you will be able to do them actually in Lab 3, I think. Yeah, because Lab 3 you will do sea-level simulation. So if you hate RTL, you can say goodbye to RTL very soon. We're going to move to sea-level simulation. And you will be able to do these studies in a simple machine. And real simulators are going to be very similar to what you build, and then, yeah. But these are very good studies to do. If you're especially starting out your research in architecture, it's always good to explore these things. Okay, very good question. So let's skip this. We're done with this. No questions on perceptron. So perceptron actually, like I built perceptron for my thesis, and I saw that it works really well compared to a global predictor that is of the same size, and you look at many different potential possibilities over here. I saw a misprediction rate reduction of 20% across many workloads, like hundreds of workloads. And I use that in parts of my thesis actually. So this is something that works well. Compared to hybrid branch predictors also actually it's very strong. But it turns out there is a better predictor that actually won the championships. The key observation it relies on is different branches require different history lengths for better prediction accuracy. Now this shouldn't be non-intuitive because we said that there is correlation between the branches, but sometimes the branch that you're correlated with is very close to you, sometimes it's far away from you, sometimes it's somewhere in between. So if you can somehow identify these things, you can reduce in one way you can reduce the interference. If you have a global predictor, it's trying to use a single history to predict everything, right? But for some branches, you don't need all of that history. And for some branches, you need even more history, right? That's the idea. How do you do that? You're not going to get it with a single history length. So partition the tables such that some tables are dedicated to smaller histories, some tables are dedicated to larger histories, and maybe use even very, very large histories, like 1,000 branches. But of course, if you have 1,000 history length, you don't build a pattern history table that's of 2 to the 1,024. That's a lot. So you need a tagged table at this point. That's why what we're going to build is going to be very tagged tables. many tag tables with different histories. Okay, basically the idea is this: have multiple pattern history tables indexed with global history registers with different history lengths, and intelligently allocate pattern history table entries to different branches. And it looks like this basically. You have a base predictor that just uses PC, history length 0. You have another table. As you can see, it's tagged, and there's a confidence bit, which we will talk about, or used bit, I think they call it over here in this paper. And you basically index it with some history length. In this case, they argue for a geometric history length. So history lengths are geometrically increasing. It's a geometric series. So basically, you can get to a very large history lengths very quickly. Let's say 1, 2, 4, 8, or 1, 4, 16, 64, depending on the constant that you multiply with. Yeah, okay, but yeah, that derailed me a little bit. But basically, this is one history length. Maybe this is shorter history length, longer history length. Let's say this is 1. This is, I don't know, 8. This is 64. This is 512, right? Those are the history lengths. And the tables look very similar. And the prediction comes from the table that basically provides with the longest history in this case. Right? I don't know if they say it over here, but in the longest history. But we're going to deconstruct that, because it turns out sometimes you don't want the longest histories. You want the most confident predictor over here. Basically, you can keep track of how well each of these tables are doing and pick the predictor that's providing you the best prediction. It's a form of hybrid predictor as well, except it's now using different history lengths in the hybrid. This is the global predictor again. Okay, so this is one example. They call the tagged and prediction by the longest history matching entry. And there's the tagless base predictor. And if you're really interested, I would recommend you take a look at these papers. I just wanted to give you a key idea. And this was the winner of there used to be branch prediction championships. I don't know if it's going to happen next year again, but this is the winner of the branch prediction championship. So this is, you have multiple tables. One of them may provide a hit. Another may provide a miss. Another may provide a hit also. So now you have two predictions, right? You have one prediction and one alternative prediction. Assuming you're picking the longest history, that assumes that longest history is the best. But that's not necessarily true, actually. In general case, longest history matching component provides a prediction. Special case, many mispredictions on newly allocated entries. So you have weak counters. So on many applications, they found out that this alternative prediction is more accurate than the predictor, the prediction. And they actually dynamically monitor this property through 4-bit counters. You can read the details here. So basically, they try to figure out which predictor is doing well. Now that's where the black magic comes in somehow, right? And you can see there's a prediction counter, 3-bit prediction counter. Was their entry recently useful, usefulness counter, and a partial tag. So this is the prediction. This is, was it useful? And you have a partial tag. So it's not a complete tag of the full PC. Okay, if you're really interested, you can take a look at these papers. But the state of the art is essentially based on these. These are the winners, and these are also implemented in real processors. Andres Sesnek also won an Intel award because of his contributions to branch prediction, as well as caching. But basically, this is an example of the winning predictor from 2016. You have a program counter, you have global history, different lengths, and you use this Tage predictor that I just described. It's a main predictor. You have a separate loop predictor on the side. And these championship branch prediction championships actually run on tight budgets. So there's a budget for these predictors. And I think this won all the budgets, although the budgets never went to extremely high budgets. But basically, there's interesting stuff over here. You basically take the prediction, and you figure out if you're confident with the prediction. So there's a statistical correction engine over here that takes into account basically the kitchen sink, I call it. You take into account global history, local history, and I don't remember what the skeleton history was, but you can look at the paper. You basically take all of that into account and basically try to overrule this predictor. As I said very early on, if your branch predictor is doing 0% accurately, then you flip the prediction and you get 100%. Right? That's what the statistical corrector is trying to do. And for many reasons, this may be doing wrong. Okay, so let me actually go a little bit more. So another direction, actually, we're trying to predict these hard to predict branches. This is a very interesting idea. As opposed to trying to build a predictor for these hard-to-predict branches. Use your predictor resources for as much as you can, but there still remain some hard-to-predict branches. What do you do with them? And this idea over here is to compute the outcome. Basically, you have a separate thread called the helper thread, customized for predicting a particular branch that you have a lot of difficulty predicting with in some other way. Basically, you pre-execute the program. And this paper describes how to build this in hardware. I'm not going to go into the detail, but let me see if there's anything else. No, there's nothing else related to this. But basically, what you do is you form in this thread, you would like, ideally what you would like is the backward slice of the branch, meaning all of the interesting instructions that are leading to the computation of the outcome of the branch. And you pick those instructions somehow. It could be formed by the compiler, it could be formed by the hardware, as this paper describes. And you build a thread. And that thread, the sole purpose of it is to execute all those instructions and get to the outcome of the branch. It's a prediction, because this thread may not execute everything. And this thread may not have all the inputs correctly, so it may actually predict the inputs to itself. But the key idea is while the main program is executing, this thread is also executing. And this thread generates a prediction for the branch, and hopefully main program actually uses that prediction. So you need to launch this thread early enough such that this prediction is generated and supplied before the main program reaches that hard-to-predict branch. That's the idea. It's called micro-threading or helper threading. You could do this for cache misses also, and we'll discuss that when we talk about prefetching, and you could employ this in existing systems, although the existing systems don't do this as far as I know. But this actually increases your accuracy even more because you're really computing the outcome of the branch now, right? You're not trying to predict with some magic. Although your thread needs to be carefully constructed. Okay, that's the idea. And if you're interested, these two papers actually cover a lot. This was the one that introduced the idea of this helper threading. They called it simultaneous subordinate micro-threading. You have a small thread that's subordinate to the main thread, basically. It's helping the main thread with those tasks. Helper threading is a much better name, I think. And this is basically looking at how do you actually do the branch prediction for very, very hard to predict branches using these helper threads. Okay, I talked about branch confidence estimation a little bit without even telling you what it is, but it's kind of obvious what it is. And this is a paper that has just won the Microtest of Time Award for this year, actually, one of the papers, that basically assigns the confidence to conditional branch predictors. The idea is very simple again. You estimate if the prediction is likely to be correct. Estimate how confident you are in the prediction. Why do you do that? Because it could be very useful in deciding many things, how to speculate. It's actually a small framework for building many things, like what predictor to choose or use, whether to keep fetching on this path, and whether to switch to some other way of handling the branch, or whether to completely switch to some other thread, right? If you figure out your confidence, you can build a better predictor, or you can build better policies as to what to do. And the idea is like this, basically. This is one example, estimator, confidence estimator. You keep a record of correct, incorrect outcomes for past n instances of the branch. Based on the correct, incorrect patterns, guess if the current prediction will likely be correct or incorrect. So this is one example here. And I don't even remember what CIR stood for, but basically you take, these are your, you get a confidence prediction based on the correct, incorrect outcomes that you stored for a given branch. And you can index that table based on the branch and global history register also. But this paper examines many other possibilities, so take a look if you're interested. So what does this enable? This enables many, many things, as I said. Actually, it's heavily used in the TAGE predictor that I mentioned earlier. It's heavily used in selecting between hybrid branch predictors. And it could be used for something like this. It's a different idea. But this paper, for example, proposes what is employed in some processors called pipeline gating. And the idea, in this case, is very simple, but the fundamental idea is very similar. Fundamental idea is obvious, maybe. You basically keep track of how many low confidence branches you have in the pipeline. Low confidence meaning you're not really confident about the prediction because you've mispredicted this branch in the recent past. If you have more than some threshold value of such low confidence branches, say, okay, I'm going to stop fetching. And the idea is to save power, right? Because if every additional low confidence branch that you add into the system in the pipeline is probably going to increase the probability that you're on the wrong path. And if you're on the wrong path, we're going to get back to this later on, you're likely wasting a lot of energy and power. And that's the idea over here. And it's very simple. If you see a low confidence branch after you predict it, you increment the counter. If the low confidence branch is resolved, you decrement the counter, and you have a fetch engine that gates the fetch based on that information. Of course, this doesn't look very interesting with a small pipeline, but think about the pipeline being a very large out-of-order execution engine. I mean, another decision could be you don't gate fetch, but you switch to another thread, right? So, okay, another application is the statistical correction of prediction that we just discussed. You basically have confidence of the branches and confidence in computed in different ways to actually correct the main predictor's prediction. Okay, I think I've gone to a natural stop over here. Any more questions? Does it sound fun? It's actually a lot of fun. Some people have gotten really rich building branch predictors while having a lot of fun. Okay, so let's take a break here. Let's take a break for, let's see, 5 past 3. I don't know if you have it over there. Yeah, like 12 minutes.
I think class ends in 5 minutes.
Yeah.
Does it?
Yeah.
Oh, okay. Now I'm actually in the other way around. Does it end in 5 minutes? It's a really natural stop, though. Okay, good. If it does end in 5 minutes, I'll take 5 questions. Otherwise, we'll break. Wow. Okay. Yeah. I have another class to teach actually. So thank you. Last time my predictor was wrong the other way around. I thought it ended at 2:30. This time my predictor is wrong for the future. You didn't correct me last time. Why did you correct me this time? I'm not saying it's bad that you corrected me because I have to go teach something else. But okay. Any other questions? Otherwise, it's a really good natural stop. And I'll see you tomorrow then. Okay.